Look up at the night sky and the mind immediately does something comforting. It assumes the sky is present. It assumes that what is visible must be happening now, at least in the same moment you are standing there, breathing, watching, letting the darkness settle around you. This is how sight feels in everyday life. When you look at a tree, you assume the tree exists in the same instant as your gaze. When you watch a passing car, you assume you are seeing it as it moves. The world seems synchronized with you. But the night sky is not part of that synchronization. The night sky is not a live scene. It is not a window opened onto a distant present. It is something quieter. It is a collection of arrivals. Every star you can see is sending you information that left long before you looked up. The sky is full of messages that began traveling earlier, crossed empty space, and only now have reached your eyes. And once you notice that, a small shift happens in the way the sky feels. It becomes less like a ceiling and more like a distance made visible. Because in space, distance is not only a separation of places. It is a separation of moments. Light does not appear instantly. It moves. And even though it moves faster than anything else we know, it still needs time. That time is usually invisible in daily life. Earth is small enough that the delay is negligible. The world around us behaves as if it is happening together. But the universe is not built on the scale of Earth. In the universe, even light cannot keep everything aligned. And because light is the main way we see anything beyond our immediate surroundings, the delay in light becomes a delay in knowledge. This is the central idea we have to hold from the beginning. What you see in the sky is not what exists now. It is what existed when the light left. The difference between those two things, between what is happening and what has arrived, may be small when the source is close. But it grows quickly and it grows without mercy. A nearby source means a small delay. A distant source means a deep delay. And eventually the delay becomes so large that you are no longer just seeing an object far away. You are seeing a different era of the universe. This is what makes astronomy so unusual. Most scientists can repeat their experiments in the present. They can change a condition, observe a response, and watch the outcome unfold in real time. Astronomy cannot do that with the sky. We cannot make the universe repeat its past so we can observe it again. We cannot pause an event that happened millions of years ago and study it from different angles. We cannot retrieve the current state of a galaxy the way we can measure the current state of a chemical reaction. We are given what arrives. We are given what survived the journey. And from that, we try to build understanding. This is why the sky is not just an image. It is evidence. And evidence always comes with limits. Because even when a signal arrives, it can arrive weakened. It can arrive altered. It can be blocked, scattered, absorbed, and reshaped by what it passes through. The universe does not send its messages through a clean corridor. It sends them through space that contains dust, gas, gravity, and other light. So what reaches us is never the entire story. It is a trace of the story. A fragment that must be interpreted. When we say we observe the universe, what we really mean is that we receive these traces and we try to reconstruct what must have been true for them to exist. We do not witness the universe like a traveler standing on a mountain. We study it like an archaeologist, working from what remains. And that brings us to the question that will guide the entire documentary. If everything we know about the cosmos comes to us from the past, then how do we talk about age in a meaningful way? Because age sounds simple until you ask what you are measuring. Are you measuring how long an object has existed? Are you measuring how long its light has traveled? Are you measuring how far back in the universe's history you are looking when you see it? These are not the same thing, but the sky can make them feel like the same thing, because distance and time are intertwined in every observation. A star might be billions of years old, yet close enough that we see it almost recently. A galaxy might be relatively young in cosmic terms, yet so far away that we see it in a very early stage, because we are seeing it as it was, not as it is. So the sky becomes a strange mixture of ages. A single glance can contain different epochs at once. One part of the sky can be showing you the near past. Another part can be showing you something that happened when Earth was still forming. And beyond that, there are signals that come from a universe that had not yet built the structures we now take for granted. This is why the night sky, when understood properly, is not comforting in the way it first seems. It is calm, yes, but it is also quietly unsettling. Because it means that the present, the true present of the cosmos, is largely hidden from us. We are surrounded by a universe whose current state we cannot directly see at great distances. We only see the past versions that have had time to arrive. And yet there is also something almost beautiful in that limitation. Because if the sky is an archive, then it is an archive we can learn to read. If light is delayed, then the delay becomes a tool. It means we can look outward and, without moving, witness earlier chapters of cosmic history, simply because the universe is large and light takes time. This is the strange gift of distance. It prevents us from seeing now, but it allows us to see then. And if we learn the rules of that gift, we can begin to build a timeline of the cosmos. Not perfectly, not completely, but honestly. A timeline grounded in what arrives. In the next chapter, we will take the first step in building that timeline, by understanding how distance becomes more than a gap in space. How it becomes a clock. How the universe turns every measurement of far into a measurement of long ago. There is a habit the mind carries everywhere. When we hear the word distance, we imagine space first. We imagine separation. A gap between one place and another. Something that could be crossed if we had enough time, enough fuel, enough patience. On Earth, this idea works. Distance is a matter of travel. If something is far, it is far in the way a city is far, measured in roads, in hours, in effort. But the universe does not treat distance the way we do. Because in space, distance is not only a gap between places. It is a gap between moments. And the reason is simple, so simple it can feel almost too plain to carry such power. Light takes time to travel. We say it easily. We hear it early in school. We repeat it until it becomes familiar. But we do not always pause long enough to let it change the way we see. Because if light takes time, then the universe is not synchronized. Not even in principle. Even if nothing blocked the view. Even if you had a perfect telescope. Even if your eyes could see every wavelength. Even if you could collect every photon that ever left a distant star. You still could not see the present state of that star. You would see the light that has arrived. And arrival is always delayed. So distance becomes a clock. Not because space itself measures time, but because the information we depend on to know anything at all must cross that space to reach us. On Earth, this is almost invisible. The planet is small enough that we live inside a comfortable illusion. When someone speaks, the sound reaches you quickly. When lightning strikes, the flash arrives almost instantly. When you look across a room, the light has traveled such a short distance that the delay does not belong to your experience. But the universe is not a room. The universe is distance taken seriously. And out there, the delay grows large enough to matter in the deepest way. It changes what knowledge means. A simple example helps. Imagine a distant ship at sea. You watch it through a telescope. You assume you are watching something happening now. But if you could measure carefully, you would notice the light from the ship needed time to reach you. Not much time, but some. A fraction of a second. On Earth, that difference is meaningless. But if the ship were not kilometers away, if it were light minutes away, light hours away, light years away, that difference would no longer be a fraction. It would be a new reality. A star that is 10 light years away is not merely far in space. It is far in time. When you see it, you are receiving information that left 10 years ago. Whatever that star is doing now is hidden behind a delay. You could imagine it changing, flaring, collapsing, vanishing entirely, and until the light of that change arrives, the sky will continue to show you the older version. This is the universe's quiet rule. You do not see what is happening. You see what has had time to reach you. And this has a strange consequence. The night sky is not a single moment spread across space. It is a layered time field. One part of the sky is closer, so it is more recent. Another part is farther, so it is older. A deep region of space is not only distant, it is earlier. So when you look outward, you are not simply seeing farther. You are seeing deeper into the past. This is where the idea of age becomes complicated, but also where it becomes possible. Because if distance creates time delay, then every observation contains a timestamp built into it. Not a human timestamp, but a physical one, the travel time of light. That travel time is not always easy to calculate, and later we will see how scientists estimate it through different methods. But the principle remains steady. The universe naturally turns space into history. And once you accept that, the sky stops being a flat image and becomes a structure you can move through. Not with your body. With your understanding. You can start close, where the delays are small enough to feel like almost now. Then you can step outward, where almost now turns into long ago. And eventually you can reach distances where the past is not measured in lifetimes, but in eras. This is why astronomers often speak as if telescopes are time machines. Not because they travel through time, but because they let us see time. They let us collect messages from earlier stages of reality, messages that have been traveling quietly through space, sometimes for longer than anything on Earth has existed. And that is also why the simplest phrase in cosmology, the speed of light is finite, is not merely a scientific statement. It is a statement about the boundaries of knowing. because it tells us that the present state of the universe is not fully accessible to us at great distances. Our knowledge is always delayed, always partial, always arriving. Yet within that limitation, there is also a remarkable opportunity. Because if the universe insists on showing us the past, then the past becomes visible in a way that no other environment could allow. On Earth, history is something we infer from remains, fossils, ruins, records. In the cosmos, history is something we can literally see if we look far enough, because the farther we look, the older the light becomes. So the same principle that prevents us from seeing the distant present gives us something else instead. A chance to witness earlier cosmic chapters as they were, not as we imagine them. But before we go too far, we need to understand one more thing. This transformation, from distance into time, does not feel natural to the human mind. We resist it. We forget it. We slip back into thinking the sky is now because that is how sight usually works. And that resistance matters. Because if we want to ask how old everything we see is, we cannot rely on instinct. We must build intuition deliberately. We must learn how the brain handles scale, and why it often fails when the universe grows beyond the human world. That is where we go next. Not deeper into space yet, but deeper into ourselves. Into the scale our minds were built to understand when we try to imagine its age. It is not because the universe is abstract. It is because we are small in a very specific way. We are built for a narrow band of reality, a thin slice of distance, a thin slice of time. Our senses and instincts evolved inside forests, plains, rivers, and weather. They evolved to recognize faces, judge danger, estimate a jump, remember a path. They evolved to survive the immediate future, not to comprehend deep history. So when we try to understand the age of the cosmos, we are not only facing a scientific challenge. We are facing a mismatch between the universe and the instrument we use to imagine it. Our minds can hold a day easily, a week, a year. We can feel the passage of time because it matches the rhythm of our bodies, sleep, hunger, recovery, repetition. We can sense years because we can compare them, childhood to adulthood, strength to weakness, the changing face of someone we know. But as time grows, it changes character. A century becomes a story we borrow from books. 1,000 years becomes an image we borrow from history. 1,000,000 years becomes a word we can repeat but cannot truly experience. And 1,000,000,000 years becomes something that sits outside the emotional machinery of the brain. It becomes a number without texture. The same thing happens with distance. We can imagine a room, a street, a city. We can imagine a flight across a country. We can imagine an ocean. Even that pushes against our sense of scale, but it remains connected to travel and effort. Then we hear the word space, and our imagination tries to keep working in the same way, like distance is simply farther roads. But space is not an extension of roads. Space is distance without landmarks. Distance without air. Distance without the cues our brains rely on to feel size. So when someone says, this galaxy is millions of light years away, the brain reaches for a familiar frame and finds nothing. The number floats. It does not attach to instinct. This is why, if we are not careful, cosmic age becomes a kind of numbness. We hear the numbers, we accept them, and we move on, without understanding what they mean. But the goal of this documentary is not to deliver numbers. It is to build a way of thinking that makes those numbers meaningful. And that requires something surprisingly simple. We need to slow down, and we need to climb. We have to build scale the way the mind learns anything new, through steps. Not because the universe is secretly small, but because our imagination needs intermediate rungs to travel across it. That is why so many explanations begin with analogies. Not because analogies are perfect, but because they create a bridge from the known to the unknown. Yet even analogies have limits. If we rely on the same metaphor too often, it stops working. It becomes a shortcut rather than a tool. It becomes a way of feeling as if we understand, without truly understanding. So instead of relying on a single metaphor, we will build something steadier. We will build an internal ladder. A progression of scale that moves outward logically, without rushing. From minutes to years. From years to thousands. From thousands to millions. From millions to billions. From nearby space to deep cosmic time. This ladder will not be used to impress you. It will be used to keep the story coherent. Because this documentary is not a collection of disconnected facts. It is a single journey, and every step depends on the step before it. If we jump too far, the journey breaks. If we move too slowly, the meaning dissolves. The pace matters. And beneath the pace is a deeper truth. The universe is not difficult to understand only because it is large. It is difficult because it violates the assumptions we carry without noticing. One of those assumptions is that now is shared. Another is that space and time are separate. Another is that observation is direct, that seeing something means knowing it. At human scales, these assumptions work well enough that we forget they are assumptions at all. But at cosmic scales, they fail. And when they fail, we have two options. We can force the universe back into human intuition, which produces comforting errors. Or we can accept that our intuition is local, and we must build a new one. Science is, in many ways, the slow replacement of local intuition with universal understanding. Not by abandoning the human mind, but by extending it. By using instruments, mathematics, careful reasoning, and most importantly, by respecting limits. Because our limits are not obstacles to hide. They are part of what makes the question meaningful. To ask, how old is everything we see, is to ask for a map of reality that can exist inside a human mind. It is to ask how a small species can reconstruct the age of a universe that does not speak in our time units, and does not unfold on our timescales. So here, early in the journey, we do something important. We acknowledge that our perception is not the universe. We acknowledge that what feels natural is not always what is true. And we acknowledge that the sky is not built to be understood quickly. It must be approached slowly, with a method that keeps us oriented. That method begins with what the universe gives us most reliably. Not a number. Not a story. A signal. Light. In the next chapter, we will stop thinking of light as mere illumination and begin treating it as what it really is in cosmology, a messenger carrying physical evidence across time. And once we understand what light can say, and what it cannot, we will be ready to take the first true step into cosmic time. Most of the time, we treat light as something simple. It lets us see. It fills a room in the morning. It paints edges onto objects. It turns the world from hidden to visible, and we move through it without thinking about the journey each ray has taken to reach us. On Earth, light feels like presence. It feels immediate. But in the universe, light is not simply illumination. It is the main way distant reality reaches us at all. It is not a decoration spread across space. It is a messenger. And what matters about a messenger is not only what it carries, but what it cannot carry. When a star emits light, it is not trying to show itself to us. It is releasing energy because of what it is, because matter inside it is hot, dense, active, changing. That light escapes the star's surface and enters space. It spreads outward, thinning as it travels, becoming fainter with distance. A galaxy emits light for the same reason, but on a larger scale. Billions of stars shine inside it. Gas clouds glow. Dust absorbs and re-emits energy. Some regions burn with new star formation. Others remain quiet, older, dimmer. Every photon that leaves is a tiny piece of evidence. Not evidence of the present moment, but evidence of a moment when that photon was created. That is the first shift we need to hold. Light is not the thing. Light is what the thing once did. And because it is a record of what happened, it has a structure we can read. Astronomers do not only collect brightness. They collect patterns within the light. They spread it into spectra, thin fingerprints that reveal chemistry. They measure its color to learn temperature. They watch its changes over time to learn cycles and lifetimes. They detect subtle shifts that reveal motion, objects moving toward us or away from us. In this sense, light becomes a language. Not a language made of words, but one made of physical signatures. It can tell us what a star is made of, because each element absorbs and emits light in its own way. It can tell us whether a galaxy is rich in young blue stars or dominated by older red ones. It can tell us whether gas is hot enough to glow in X-rays, or cool enough to hide in darkness unless it is traced by something else. And sometimes, light can tell us about gravity itself, because gravity bends space, and space bends the path of light. But the second shift is just as important as the first. Light is always incomplete. Even if a source emits a perfect story, we do not necessarily receive it intact. Space is not empty in the simple way we imagine. Between us and a distant galaxy, there can be dust that absorbs certain wavelengths. There can be gas that scatters light. There can be regions where light is reprocessed, changed in character, re-emitted at different frequencies. There can be gravitational fields that distort light, magnify it, split it into multiple images, or stretch it into arcs. There can be nearer sources that drown it out. And then there is the simplest limitation of all. Distance. Light spreads. It thins. Most of it misses us completely. A telescope does not bring objects closer. It collects a slightly larger fraction of the photons that happen to arrive. So when we look at deep space, we are often working with very little, faint signals gathered over long exposures, cleaned and calibrated, interpreted with care. This is why cosmology is not a science of direct sight. It is a science of careful inference. We receive a limited message and ask what must be true for that message to exist. But even before we infer anything, we have to accept the most basic fact about the messenger. It travels. And because it travels, it arrives late. No matter how advanced our instruments become, they cannot exceed the messenger's speed. They cannot reach into deep space and pull back what is happening right now. They can only receive what has had time to cross the distance. This is where many people make an unconscious mistake. They imagine a telescope as a powerful eye that sees farther, and therefore sees more. But what it truly does is more subtle. It allows us to receive older messages with greater clarity. A telescope does not defeat time. It obeys time. It does not collapse the delay. It simply collects more of what the delay delivers. So the universe comes to us in layers. Near objects deliver recent messages. Far objects deliver older messages. And very far objects deliver messages from eras when the universe itself was younger, when galaxies were different, when structures were still forming. This is the quiet truth that changes the meaning of looking up. We do not look into space the way we look into a landscape. We look into a history whose pages are arranged by distance. And once we begin to treat light this way, as a messenger traveling through time, then age becomes something we can begin to define with honesty. Not as a feeling. Not as a metaphor. But as a relationship between distance, travel time, and the state of the universe when that light was emitted. Still, we need one more step before the timeline becomes usable. We need a unit that ties distance to time in a natural way, one that forces us to stop thinking of space as mere separation. A unit that quietly contains the idea of travel. That unit is so common that we often forget its meaning. The light year. In the next chapter, we will treat the light year not as trivia, but as the first true bridge between what we see and when it was real. A light year is one of those terms that can sound more dramatic than it is. It has the word light in it, which makes it feel like speed. And it has the word year in it, which makes it feel like time. So people often assume it must be a measure of time. But a light year is a measure of distance. It is simply the distance light travels in 1 year. And the simplicity of that definition is exactly why it matters. Because hidden inside it is a quiet merging of two ideas we keep separate in ordinary life: space and time. On Earth, distance is distance. You measure it in meters, miles, kilometers, units that say nothing about how long it takes to cross them. Travel time depends on your speed. A long road can be crossed quickly in a car or slowly on foot, but the distance itself remains the same. In the universe, that separation breaks down. Not because distance changes, but because the messenger that carries almost all information, light, does not travel instantly. It travels at a constant speed. And that constant speed ties distance to time in a way that cannot be ignored. So when an astronomer says something is 1,000 light-years away, they are not only describing how far it is in space. They are also describing, whether they say it aloud or not, how far back in time we are seeing it. 1,000 light-years means the light took 1,000 years to reach us. Which means we see the object as it was 1,000 years ago. In daily life, 1,000 years is beyond personal memory. It belongs to history. So even at that distance, the sky stops feeling like a present scene and begins to feel like a record. And then the distances increase. Millions of light years. Hundreds of millions. Billions. At those scales, we are no longer talking about human history. We are talking about planetary history, biological history, cosmic history. So the light year becomes more than a unit. It becomes a way to orient yourself in the universe's timeline. It is one of the first tools that allows us to take a concept that is otherwise invisible, light travel time, and turn it into something we can think with. But we have to keep one essential distinction clear, otherwise the story becomes confused. The age of the light is not automatically the age of the object. If you see a distant galaxy whose light has been traveling for 1 billion years, you are seeing it as it looked 1 billion years ago. That does not mean the galaxy is only 1 billion years old. It might contain stars that were already old at the time the light left. It might have been forming for billions of years before that moment. What the travel time gives you is not the object's entire age. It gives you a timestamp. It tells you which chapter of the object's story you are witnessing. This is a subtle but important point. Because the question we are exploring, how old is everything we see, can be answered in more than one way, depending on what we mean by old. Sometimes we mean, how long has the object existed? Sometimes we mean, how long has its light been traveling? Sometimes we mean, how far back into the universe's development are we looking when we observe it? These meanings overlap, but they are not identical. And a light year mainly serves the second and third meanings. It tells you about the age of the message. And it often tells you, indirectly, about the age of the universe at the time that message was created. Because the farther we look, the older the light becomes, and the younger the universe was when that light began its journey. At some point, this becomes more than a curiosity. It becomes a method. If the universe is large enough that we can see billions of years into the past, then the universe itself becomes an experiment we cannot repeat but can still study. We can observe different distances and see different eras. Not because those eras are still happening now, but because their light is still arriving. It is like standing in a library where the shelves are not arranged by author or subject, but by time. The closest shelves contain the most recent pages. The farthest shelves contain pages written in a much earlier universe. And the light year is the unit that tells you where you are standing in that library. But there is another reason the light year matters. It forces us to accept something the mind resists. The universe is not built around us. It does not arrange itself so that we can see it comfortably. When we say a billion light years, we are naming a distance that is almost impossible to imagine in the body. And yet, it is real. It is part of the structure we inhabit. So the light year becomes a kind of discipline. It asks us to keep expanding our intuition without losing clarity. And it becomes the first step toward a deeper idea, that the sky is a layered time field, and every direction holds a different depth of history. Still, the best way to make this real is not to jump immediately to galaxies and the early universe. The best way is to begin with delays that are small enough to feel. Because when something is only minutes old, the idea of delayed reality becomes tangible. It becomes something you can almost sense. So we start close. We start with the light that defines our days. The light from the sun. In the next chapter, we will look at the nearest time delays, minutes, then hours, and use them as the first rung of the ladder that will carry us outward into deep cosmic age. If you want to understand cosmic time, you do not begin with galaxies. You begin with something so familiar that it almost feels too simple. You begin with the light that makes morning. The sun. Sunlight feels immediate. It arrives without effort. It fills rooms, warms skin, creates shadows, and convinces the mind that the world is happening in synchrony with our senses. But even here, at the center of our daily life, the universe refuses to be truly instantaneous. The light from the sun takes time to reach Earth. Only minutes. So few that the difference doesn't alter a conversation or a decision. It does not change how we plan our day. It does not change how we experience the warmth on our face. And yet it matters, because it reveals the rule that will govern everything else. When you see the sun, you are not seeing the sun as it is in this exact moment. You are seeing the sun as it was when that light left its surface. In ordinary life, that sounds almost meaningless. A few minutes feels like nothing. But the universe is not asking us to treat it as a dramatic gap. It is asking us to treat it as a principle. Because if the delay exists here, then it exists everywhere. And if it exists everywhere, then now is not something the sky can reliably offer. It is something only your immediate surroundings can provide. There is a quiet thought experiment that makes this clear. Imagine that the sun were to change suddenly, something extreme, something impossible in ordinary physics, but imagine it anyway. If the sun vanished, Earth would not know immediately. The sky would not darken in the same instant. The light already in transit would continue to arrive, as if nothing had changed. For several minutes, we would still see the older sun. We would still live inside the older reality. Then, only when the final wave of light reached us, would the new reality become visible. Again, this is not a prediction. It is an illustration. It shows that what we call seeing is not direct contact. It is receiving a message that has already begun its journey. And once you accept that, you can begin to see the solar system as a training ground for cosmic time. Because the solar system is large enough that delays become noticeable, but still close enough that your mind can hold it. Look at the moon. Moonlight is not its own light. It is sunlight reflected from a surface of dust and stone. That reflected light also takes time to reach you. The delay is small, but real. When you see the moon, you see it slightly earlier than the moment you're standing in. Then consider the planets. The light we see from Venus, Mars, Jupiter, it is sunlight reflected from them, or emitted as heat, or glowing in bands we cannot see with our eyes. And that light is older still. Depending on where the planets are, the delay can be many minutes, sometimes longer. In the age of radio communication with spacecraft, this is not a philosophical idea. It is a practical limit. Commands do not arrive instantly. Responses do not return instantly. Space exploration is a conversation with built-in silence. And inside that silence is the same reality we are trying to understand on a cosmic scale. Distance creates delay. Delay creates a difference between what is happening and what we can know. In the solar system, this difference is manageable. It feels like a small inconvenience. A pause in communication. A waiting time for signals. But it teaches the mind the correct habit. It teaches you to stop assuming that observation is immediate. It teaches you that seeing is a process. And it also introduces a deeper point that will become important later. The universe is not merely far away. It is far away in a way that changes the meaning of information. In the solar system, we can still send probes. We can still arrive physically. We can still touch things, sample rocks, measure magnetic fields directly. So we might be tempted to think that deep understanding is always one mission away. But once we leave the solar system, that comfort disappears. We cannot go to the stars easily. We cannot touch galaxies. We cannot place instruments inside the early universe. Most of what we will ever know beyond our local neighborhood must come through the messenger that can cross those distances on its own. Light. So chapter 6 is not just about the sun and the moon and the planets. It is about accepting the first rung of the ladder. It is about realizing that even the nearest cosmic light is already old, and that old is not a special condition reserved for deep space. It is built into every observation. And once the mind accepts minutes, it becomes possible to accept years. Because the next step outward is where the delay becomes too large to ignore. When we look at the nearest stars beyond the sun, we are no longer dealing with minutes or hours. We are dealing with light that has been traveling for years. And in that step, the sky begins to reveal its true nature, not as a present dome, but as a depth of time. That is where we go next. Once you leave the solar system behind, something changes that is easy to underestimate. Inside our planetary neighborhood, time delay is a detail. A few minutes here, an hour there. It is the kind of distance that still feels connected to travel, because we have sent machines across it. We have crossed it with probes, we have mapped it with signals, we have learned to wait for responses. But the space between stars is not an extension of the space between planets. It is a different category of emptiness. It is so large that the delay is no longer a practical inconvenience. It becomes a fundamental condition of what it means to observe. When you look at the nearest stars, you are not looking at something far away in the ordinary sense. You are looking at something that you are seeing years late. This is the first distance where the delay becomes emotionally real, if you let it. Because a year is not an abstract unit for the human mind. A year is a cycle we live inside. It carries seasons, memories, aging. It is long enough to hold change. So when you say that the nearest star's light takes years to arrive, the number is not just measurement anymore. It becomes a gap you can feel. Consider what it means. A star shines. It releases light continuously. That light leaves in every direction, and a tiny portion of it, an unimaginably small fraction, happens to cross the space where Earth will be, crossing the exact place where your eyes might one day look up. But that crossing does not happen instantly. The light has to travel. It crosses the darkness between stars, darkness that is not merely night, but a deep, cold emptiness where there is almost nothing to slow it down, and still it requires years. This is where the sky begins to become what it truly is, a collection of messages in transit. And here the idea that we see the past stops being a clever statement and becomes a practical fact. Because stars change. Not quickly in the way living things change, but they do change. They pulse. They rotate. They flare. They shed material. They brighten and dim. Some have cycles that repeat. Some have storms on their surfaces. Some release sudden bursts of energy. When we observe a nearby star, we are not observing its present state. We are observing the state that existed when the light left. It might be only a few years ago, but years are enough for a story to move forward. Years are enough for a star's surface to flare, for a companion star to eclipse it, for activity to rise and fall. And beyond the nearest stars, that delay grows steadily. 10 years. 50 years. 100 years. At that point, something subtle happens. The sky begins to contain events that occurred before you were born. Not because the stars are ancient in themselves, they often are, but because the light you are seeing is older than your life. And this is where a new kind of humility enters the story. We often treat the sky as a fixed background, unchanging, dependable, always there. But that stability is partly an illusion created by our short lives. Stars do not appear to change much because we do not watch them long enough in human time to notice the slow evolution. But even the changes that happen on shorter timescales are delayed to us, and the larger truth remains: we do not have direct access to the present state of any star except the one we orbit. Even in our local neighborhood, the universe is slightly out of reach. The nearest stars represent the first real separation between human time and cosmic communication. And there is another reason this chapter matters. Because once we accept that starlight arrives years late, we must accept that the sky is not a single uniform layer. It is depth. Some stars are closer, so their light is less delayed. Some are farther, so their light is more delayed. The sky becomes a subtle map of time differences. And yet to the naked eye, all these stars seem to sit on the same flat surface. This is a common deception of perception. Your eyes are excellent at detecting patterns and brightness, but they are not designed to measure astronomical depth. They flatten the sky into a dome. They turn a three-dimensional universe into a two-dimensional field of points. It is only when you bring the concept of light travel time into the picture that the dome breaks open. A star is not up there. It is out there. And out there means back then. So with the nearest stars, we begin to learn the documentary's central skill: to look at a point of light and silently translate it into a time delay. Not as a gimmick, but as a new instinct. And as that instinct forms, the sky becomes something else. It becomes a record in motion. Because the light you receive tonight is not the only light that exists. The star is continuing to emit new light right now, light that will reach Earth years from now. And the light you are seeing now left years ago. So the universe is always layered with different versions of the same source, spread across space like a continuous ribbon of time. This is difficult to picture, but it is one of the most important images to hold. Imagine a star as a speaker, broadcasting outward in every direction. The sound is not sound, it is light. And it does not fill space instantly. It expands outward like a growing sphere. At each distance, the sphere contains a different moment of the star's story. Where you are standing now, on Earth, you intersect that sphere at a particular time slice. You do not choose the slice. Distance chooses it for you. This is what distance does. It selects which moment you can access. And this selection becomes even more powerful as we go farther out, because the delays become not just years, but tens of thousands of years, then millions, then billions. But before we jump ahead, the journey has to remain coherent. So we take the next step outward carefully. The nearest stars give us years. The next scale, the scale of our galaxy, gives us tens of thousands of years, even within a single glance across its disk. And there, the sky becomes not only delayed, but vast enough that a single object, the Milky Way, contains many different times at once. That is the next rung of the ladder. In the next chapter, we will enter the Milky Way as a time structure, and begin to feel what it means to look across a system so wide that its light can be older than civilizations. The nearest stars teach us something important. Light is delayed, and delay is real. But the Milky Way teaches us something deeper. It teaches us that delay is not only something that happens between us and distant objects. Delay can exist inside a single system. Because our galaxy is not a point of light. It is an environment, wide enough that different parts of it are separated by tens of thousands of light years. And that means that when we look across it, we are not seeing one moment. We are seeing many moments at once. From the ground, the Milky Way looks like a pale band, a soft smear across the sky. It feels almost like weather, something atmospheric, something near. But it is neither near nor atmospheric. It is structure. It is a disk of hundreds of billions of stars, gas and dust arranged into spiraling patterns, with a dense central region and a faint outer halo. It contains regions where stars are being born and regions where stars have been dying for billions of years. It contains quiet stretches and violent neighborhoods. And it contains, at its center, an object so compact and massive that even light cannot easily escape its influence. Yet even without focusing on those details, the Milky Way gives us a new way to feel time. Because the galaxy is large enough that looking across it is like looking across eras. If one side of the Milky Way is tens of thousands of light years away, then the light from that side has been traveling for tens of thousands of years. That is not a metaphor. That is the physical meaning of the distance. So when you look toward the crowded center of the galaxy, you are receiving a message that began its journey long before modern society. Long before written history in many places. Long before the world you recognize was built. And when you look toward the nearer regions of the Milky Way, the light is more recent, still old in human terms, but different in degree. This is the first time in our journey where a single object contains a significant range of light travel times. The Milky Way is not one distance away. It is a spread of distances. And because distance becomes time, it is also a spread of times. So in a single glance, without moving, you can see a nearby star's recent past and, in the same sky, receive light that left another part of the same galaxy when human culture was in a completely different stage. This realization changes how you should think about the present universe. If even our own galaxy is not visually present to itself, then the universe as a whole certainly is not. We are always assembling a picture from time-separated pieces. And the Milky Way forces us to confront another difficult fact. We are inside the thing we are trying to understand. On Earth, it is easy to map a city from the outside, to understand its shape because you can step back. But in a galaxy, we cannot step outside. We are embedded in the disk, surrounded by stars and dust. We do not have a clear overhead view. So when we look at the Milky Way, we are not looking at an object placed neatly in front of us. We are looking through it. We are looking along crowded lines of sight filled with foreground stars, background stars, clouds of dust that block visible light, and regions that glow only in wavelengths our eyes cannot see. This makes observation harder, but it also makes it richer. Because the Milky Way is not just a system of stars. It is a laboratory where we can study many stages of stellar life at once, not because time has been sped up, but because the galaxy is large enough and complex enough that different regions are in different phases. Some regions are nurseries, cold clouds collapsing, young stars igniting, light emerging from dust. Other regions are old neighborhoods where stars have settled into long stable lives. And beyond the disk, in the halo, there are older populations still, stars and clusters that may have formed early in the galaxy's history, carrying chemical fingerprints from a time when the universe contained fewer heavy elements. So the Milky Way becomes a kind of archaeological site. Not one frozen moment, but a layered record of formation. And crucially, it shows us that age can be approached in more than one way. We can talk about the age of the light we receive from different parts of the galaxy. We can talk about the age of the stars themselves. We can talk about the age of structures, spiral arms, clusters, the central bulge. These are different kinds of age, and the galaxy contains all of them at once. But for now, the most important contribution of the Milky Way to our journey is the feeling it gives us for scale. Because tens of thousands of years is still small compared to cosmic history, but it is large compared to human time. It is large enough to break the illusion that the sky is now. And it prepares the mind for the next step outward, where the delays become not tens of thousands, but millions. There is a particular moment that captures this transition beautifully. It comes when we stop looking inward through our own galaxy and instead look at a galaxy beyond it, an entire island universe, far enough away that its light began traveling toward us before most of what we call human history existed. And that galaxy is close enough to see in the sky, faintly, with the naked eye under dark conditions. Andromeda. When we move from the Milky Way to Andromeda, we move from the time delays of civilizations to the time delays of species. We move from history into prehistory. In the next chapter, we will take that step, and feel what it means to see a galaxy as it was millions of years ago, as if the universe is quietly offering us an ancient photograph, still arriving, still readable, still incomplete. There are moments in astronomy that do not feel like discoveries. They feel like perspective. And one of the quietest, most powerful shifts happens when you realize that you can see another galaxy with your own eyes. Not through a telescope. Not through a screen. Just by standing under a dark sky and looking carefully. A faint, soft smudge. Easy to miss if you do not know where to look. That smudge is Andromeda. An entire galaxy. A structure so large that our minds struggle to hold it as a single object. Billions of stars bound together by gravity, shaped by rotation, surrounded by dark matter, carrying its own internal history. And yet it sits in the sky as a small blur. This is one of the universe's strangest tricks, to compress an immense reality into a fragile point of light. But the deeper reason Andromeda matters in this story is not its size. It is its time. Because when you look at Andromeda, you are not seeing it as it is now. You are seeing it as it was when the light left it. And for Andromeda, that light has been traveling for millions of years. That number can be said quickly. It can be repeated without weight. But if you pause and allow it to settle, it changes the meaning of the sky. Millions of years is not human history. It is deeper than empires. Deeper than languages. Deeper than almost everything we think of as the past. When the light you see tonight began its journey from Andromeda, modern humans were not living the lives we live now. The world was different in ways that do not fit neatly into memory or story. So to look at Andromeda is to look across an interval so long that the human mind cannot naturally hold it. It is to see before the world you recognize. And this is where the documentary's central idea becomes something more than a concept. Because up to now, we have been building the ladder carefully. Minutes, sunlight and the solar system. Years, the nearest stars. Tens of thousands of years, the width of our galaxy. Now, millions. This is the first distance where the sky becomes ancient in a way that feels almost foreign. And there is a quiet tension inside that realization. Because Andromeda is not a static picture. Andromeda is moving. It is approaching. It is part of a gravitational dance with the Milky Way that will unfold across enormous time scales. But what we see of Andromeda is not the latest step in that dance. It is a delayed frame. A still arriving image from a time long before our current moment. So when we talk about Andromeda's future, its eventual interaction with the Milky Way, we must remember that our view of Andromeda is already behind. We are always a little late to the universe. And this lateness is not a flaw in our instruments. It is built into reality. At this point, it helps to hold a new mental picture. Imagine that every object in space continuously emits an expanding shell of information. A sphere of light growing outward at the speed of light. That sphere is not merely light filling space, it is history moving away from the source. Each distance from the source corresponds to a different moment in the source's past. Close by, the sphere carries recent moments. Far away, it carries older moments. And we, on Earth, intercept that sphere at one particular radius, one particular time slice. So the Andromeda we see is not the whole Andromeda. It is Andromeda at the moment whose light is reaching us now. And what makes this profound is that Andromeda is not just one object. It is a system with internal diversity, older stars, younger stars, dust lanes, clusters, core structures. When we see it, we are seeing a composite message from billions of sources, all delayed by the same overall travel time, yet containing many different internal ages. So millions of years ago, describes the age of the light as it left the galaxy. But the stars inside Andromeda may be billions of years old. This is where cosmic time becomes layered. And that layering matters, because it teaches us what our question truly demands. If we are asking, how old is everything we see? We are not asking for one simple timeline. We are asking for an understanding of multiple clocks. The travel time of light. The age of objects. The age of the universe at the time we observe them. The age of structures as they form and evolve. Andromeda forces this complexity into view. It is far enough that its light is ancient in human terms, but close enough that it still feels like a single object rather than a distant abstraction. It becomes a bridge between the world of stars and the world of galaxies. And once we cross into the world of galaxies, the ladder continues upward quickly. Because beyond Andromeda lie other galaxies, and beyond them clusters of galaxies, and beyond them the cosmic web, structures so large that their scale is measured not in light years, but in tens and hundreds of millions of light years. At that point, we are no longer talking about the age of light in relation to human history. We are talking about the age of light in relation to Earth's long history, and beyond that, the history of the universe itself. And here the meaning of present sky collapses completely. Because if Andromeda is millions of years delayed, then deeper space is delayed by tens of millions, hundreds of millions, billions. A glance upward becomes a view across cosmic eras. The universe becomes a mosaic of time. But before we move farther, we need to ask a crucial question. If the sky is so delayed, then how do we avoid confusion? How do we organize what we see into a coherent picture? How do we map a universe where every direction holds a different time slice? The answer begins with structure. Not with individual objects, but with patterns, how galaxies are arranged, how they cluster, how the universe builds architecture on enormous scales. Because once we understand that architecture, we begin to see that cosmic age is not only hidden in the light travel time. It is also written into the shape of the universe itself. In the next chapter, we will move from single galaxies to the larger patterns they form, and begin to see the universe not as scattered islands, but as a connected web, shaped by gravity and time. Once you begin to accept that the sky is layered in time, a second realization follows almost naturally. The universe is not arranged the way we once assumed. It is not a smooth field of galaxies spread evenly through space, like distant lamps placed at regular intervals. It is structured. And the structure is not subtle. If you step back far enough, far beyond the scale of individual galaxies, you begin to see a pattern that looks less like a random scattering and more like architecture. Galaxies gather. They form groups. They form clusters. They form long chains and walls. They trace filaments across enormous distances, leaving behind wide regions that contain almost nothing. This is the cosmic web. It is one of the most important ideas in cosmology, not because it is visually dramatic, but because it reveals that the universe has a history of growth. A smooth universe would suggest a simple story. A structured universe suggests a story of change, of matter pulling itself together over time, of small differences becoming large ones, of gravity shaping what was once nearly uniform into something intricate and uneven. And this matters for our question about age. Because the age of the cosmos is not only something you infer from distant light. It is also something you can sense, indirectly, in the maturity of structure. The universe has not always looked the way it looks now. If you could go back far enough, the galaxies would not be arranged into the same complex web we map today. The clusters would not be as massive. The filaments would not be as developed. The voids would not be as sharply carved. Structure takes time. Which means structure is a kind of clock. But to appreciate that, we have to first let go of another human habit. We tend to imagine the universe as a thing that exists all at once, equally real in every direction. We imagine it as an object that could be photographed from the outside. In reality, we are inside it, receiving light from different distances, different times, at the same moment. So when we map the distribution of galaxies, we are not mapping a single moment frozen in time. We are mapping a layered history. Nearby regions show us the universe in a more mature state, more recent, more developed. Farther regions show us the universe earlier, when structures were younger, less evolved, still assembling. So the cosmic web is not just a pattern in space. It is a pattern across time. A record of how gravity has worked over billions of years. Yet it would be easy to misunderstand this, to think the cosmic web is something delicate and purely theoretical. It is not. It is robust enough that we can detect it in multiple ways. We can count galaxies in large surveys and see where they cluster. We can measure how light from distant objects bends through gravitational fields and infer where mass is concentrated. We can map hot gas in clusters using X-ray observations and see where matter pools. Different methods, different messengers, but the same general picture emerges. Matter is not evenly spread. It is organized into a connected network. And inside that network is another profound shift in perspective. Because the cosmic web is not shaped only by what we can see. Much of the mass that creates the web does not shine. It does not glow like stars. It does not emit light in the way gas and plasma do. It reveals itself mostly through gravity, through its influence on how things move and how light bends. This invisible mass is what we call dark matter. And whether or not we fully understand its nature, its role in the structure of the universe is clear. It provides the scaffolding. The visible universe is, in a sense, the decoration on a deeper structure we cannot directly see. Which means our observations are always incomplete in a particular way. We see light, but light does not show us all the mass. We see galaxies, but galaxies do not mark all the matter. So when we look at large-scale structure, we are learning not only about where the universe is dense and where it is empty. We are learning about the relationship between what is visible and what is real. And this relationship is essential to understanding age, because age in cosmology is tied to processes we cannot watch directly. We cannot watch a filament form over billions of years. We cannot watch a cluster assemble in real time. We infer these histories from patterns we see at different distances, at different look-back times. So the cosmic web becomes a narrative tool. It shows us that the universe has been transforming from a simpler early state into a complex present state. And that transformation implies a timeline. But this raises an important question. If structure grows, then what did it grow from? The web did not appear fully formed. Clusters did not simply exist. Filaments had to emerge from something less organized. So the next step in our journey is to understand what the early universe was like before this structure took shape. Not in detail, not as a textbook. But in the calm, essential sense. What conditions existed early on that allowed matter to begin gathering into the web we see now? Because once we understand that, we will understand that cosmic age is not just how long light has been traveling. It is how long the universe has been evolving from near uniformity into structure. That evolution begins with something deceptively small. Tiny differences. Almost nothing. And yet, over cosmic time, those tiny differences became galaxies, clusters, filaments, everything. In the next chapter, we will explore how small early variations turned into large structures, and why the universe's age is written into that slow amplification. But because it would be missing the very idea of objects as we know them. No galaxies. No stars. No clusters. No long filaments of matter tracing a cosmic web. In the beginning of this part of the story, before structure matured, the universe was closer to smooth. Not perfectly smooth, but smooth enough that the differences were subtle, almost easy to dismiss. And yet those differences mattered more than anything that came later. Because the universe we see today, its entire architecture, grew out of tiny irregularities. Small differences that became everything. This is one of the deepest patterns in nature. Large structures often begin as small imbalances. A slight temperature change becomes a wind. A tiny shift in pressure becomes a storm. A small crack becomes a fracture. A barely noticeable preference becomes a dominant path. The universe is not exempt from this rule. If matter had been spread with perfect uniformity, gravity would have had nothing to work with. Every region would pull equally on every other region, and the universe would remain featureless, expanding and cooling without ever condensing into the rich structures we see. But the early universe was not perfectly uniform. It contained minute variations, slight differences in density, tiny departures from average. Regions that were a fraction more crowded with matter than their surroundings. These differences were extraordinarily small. But gravity is patient. Gravity does not require drama. It does not require a sudden push. It only requires that there be something slightly greater somewhere, some region that pulls a little more strongly, some place where matter drifts inward rather than outward. Over time, even the smallest advantage can grow. Matter begins to fall towards slightly denser regions. Those regions become denser. Their gravity grows stronger. More matter falls in. The process repeats. And slowly, what began as a nearly smooth universe develops texture. The important thing to notice is the timescale. This is not a quick transformation. It is not a sudden assembling. It is a gradual deepening of contrast, happening over hundreds of millions and then billions of years. Structure formation is the universe performing a slow amplification. And because it is slow, it becomes a clock. A universe that has had more time will show more developed structure. A universe that is younger will show less. So when we look out into space, and therefore back into time, we are not only looking for older light. We are looking for earlier structure. We are looking for a universe that has not yet had time to fully organize itself into the patterns we see nearby. This is one of the most powerful ways the universe lets us read its age. Not just through the travel time of light, but through the maturity of what that light reveals. But there is another layer to this story, one that complicates it in a quiet way. Because not all matter behaves the same. The matter that makes stars and planets, the ordinary matter we are made of, interacts with light and with itself in ways that can create pressure, heat, and resistance. Gas can cool. It can compress. It can form clouds. It can ignite into stars. But there is another component in the universe that does not behave like gas. It does not emit light. It does not absorb light. It does not seem to collide and heat in the same way. It mostly announces itself through gravity. This is dark matter. Whether we fully understand what it is still part of the unanswered story. But its role in structure formation is clear. It begins to clump early and provides the gravitational scaffolding that ordinary matter later falls into. So the cosmic web is not just a pattern of glowing galaxies. It is the visible outcome of a deeper gravitational structure. The universe's architecture is built first in the invisible, and then later decorated with light. This matters because it explains something we will keep encountering. The universe often reveals itself indirectly. We do not always see the main actors. We see their effects. We see patterns in light that imply the presence of mass. We see motions that imply gravitational pulls. We see distortions that imply unseen structure. Cosmology is full of these indirect readings, because the universe is too large and too old to be studied by direct experiment. So when we say small differences became everything, we are describing both a physical and a methodological truth. Physically, the universe's large-scale structure grew from tiny early variations. Methodologically, our understanding grows from tiny signals, faint traces, amplified by careful interpretation until a coherent picture emerges. And now we come to an essential transition. If the universe's structure grew from small differences, then those differences must have existed early. So how far back can we trace them? How early can we observe the conditions that seeded everything? And if our entire knowledge arrives through light, what is the oldest light we can ever see? This is where the story begins to approach one of the most important boundaries in all of cosmology. A boundary not made of stone or matter. A boundary made of visibility. A time when the universe was so hot and dense that light could not travel freely. a time before the universe became transparent. To understand the age of the cosmos, we need to understand what we mean by the age of the universe itself, what we measure, how we define it, and why the word beginning has a specific meaning in physics. That is the next step. In the next chapter, we will slow down and clarify what the age of the universe really refers to, and why our definitions must be precise before the deeper history can come into view. By this point in the journey, one idea has become unavoidable. The sky is not a single moment. It is a lag record. Distance becomes a clock because light takes time to travel, and the farther we look, the earlier we see. Structures grow slowly, so their maturity carries a kind of timestamp. The universe is not only large, it is old, and it shows us pieces of its past whenever we observe it. So it might seem natural to ask, now, for the number. How old is the universe? But the moment we ask for a number, we also have to ask something quieter and more careful. What exactly do we mean by age? Because in daily life, age is simple. A person's age is the time since birth. A tree's age is the time since it began growing. Age is a single counter that starts at a clear moment and increases steadily. The universe does not offer such a clean starting point in the same way. Not because scientists are confused, but because the universe is not an object inside time. It is the context in which time unfolds. So when we say the age of the universe, we are not talking about how long something has existed inside a larger clock. We are talking about how long the universe itself has been in its current evolving state, how long it has been expanding, cooling, and changing from an early dense condition into the vast, structured cosmos we observe today. That definition sounds simple, but it carries several important implications. First, the age of the universe is tied to the universe's expansion. This is not an optional detail. It is central. If the universe is expanding, then earlier it was denser. If earlier it was denser, then there is a kind of starting era when it was extremely hot and compact. The age is measured from that early era to now. Second, now has to be defined carefully. On Earth, now means the time you are reading this sentence. In cosmology, now often means the current age of the universe here, in our region, measured in our cosmic time. But because information arrives at different times from different distances, we can never observe the universe's now everywhere at once. We cannot take a universal snapshot. So the age of the universe is not something we read directly from the sky like a label. It is something we infer from the universe's behavior and from the patterns we observe. Third, we must distinguish between different kinds of age that can easily be confused. Because when people say how old is everything we see, they often mix three ideas. The age of the light, how long the photons traveled before reaching us. The age of the object, how long a star, galaxy, or structure has existed. The age of the universe at the time, how old the universe was when that light was emitted. These are related, but they are not the same. And the documentary's job is to keep them disentangled, so the story stays coherent. Let's take a simple example. A galaxy might be 10 billion years old today. But if it is so far away that its light has been traveling for 8 billion years, then we do not see it as it is today. We see it as it was 8 billion years ago, when it might have been much younger, more chaotic, still forming. In that case, the light is 8 billion years old when it reaches us. The galaxy could be older than that in absolute terms. The universe itself was younger by 8 billion years at the time the light left. So which age are we talking about? All three can matter, depending on the question. When cosmologists give a number for the universe's age, they are usually referring to something specific. The time elapsed since the early hot, dense state described by the Big Bang model, measured in cosmic time, inferred from expansion and observation. That is the age of the universe. But it is not the only age we will encounter. When astronomers talk about the age of a star, they use stellar evolution models, composition, brightness, and how the star's life stage fits into long-known patterns. When they talk about the age of a galaxy, they look at its stellar populations, its structure, its rate of star formation, and the chemical enrichment of its gas and stars. When they talk about the age of structures like clusters and filaments, they look at how matter gathers over time, how the cosmic web matures, and how simulations match observation across different look-back times. So age in cosmology is not one tool. It is a toolkit. And it is used differently depending on what you are measuring. But there is another complication, one that is essential to understand if we want to avoid false certainty. We cannot measure the age of the universe with a single direct method. Instead, scientists infer it by building a consistent story that matches multiple kinds of evidence. They measure the expansion rate. They study the oldest light. They examine the distribution of galaxies and the growth of structure. They compare models to what we observe at different distances, which means different times. And when these different approaches agree, we gain confidence. When they do not agree, we gain a new kind of knowledge, not an answer, but a clue that something in our story may be incomplete. So the age of the universe is not just a number. It is a test of whether our understanding of the cosmos is coherent. If our measurements and models do not fit together, the universe is telling us something important, perhaps about new physics, perhaps about hidden assumptions, perhaps about the limits of our current tools. This is why the question "how old is the cosmos?" carries weight. It is not simply curiosity about the past. It is a way of checking whether the universe we describe is the universe we inhabit. And now, with this careful definition in place, we are ready to approach one of the most crucial boundaries in the entire story. If the universe had an early era when it was hot and dense, then there must have been a time when light could not travel freely, when the universe was opaque, filled with charged particles that constantly scattered photons. At some point, the universe cooled enough for light to finally move through space without being trapped. The first light that could travel freely is still out there. It has been traveling ever since. And it forms the oldest visible signal we can detect. In the next chapter, we will reach that boundary. We will meet the oldest light we can see, and understand why it is not just a relic, but a horizon that defines the edge of our visual access to the universe's beginnings. There is a limit to what ordinary sight can reach. Not a limit created by technology, or by the weakness of our instruments, but a limit built into the universe's early conditions. If you travel far enough back in time, far enough out in space, you eventually arrive at a moment when the universe did not allow light to move freely. And that moment creates a boundary for everything we can ever observe with light. It is one of the most important ideas in cosmology, and it is strangely quiet. Because it does not announce itself as a wall. It announces itself as a fading. A soft horizon. A point beyond which the universe stops being transparent and starts being fog. To understand this boundary, it helps to imagine the early universe not as empty darkness, but as the opposite. A dense, hot environment filled with energy, matter, and constant interaction. In the earliest stages after the Big Bang, the universe was not a collection of separated stars and galaxies. It was a kind of glowing plasma, an ocean of charged particles. Electrons were not bound calmly to atoms. They moved freely, and their freedom mattered. Because free electrons scatter light. When a photon tries to pass through a region filled with free electrons, it does not travel far before it is deflected. It bounces. It changes direction. It loses the possibility of a clean straight path. So even though light existed, it could not travel through space in the way we imagine light traveling now. It was trapped in a sense, not by walls, but by constant collision. This means that if you were somehow present in that era, you would not have been able to see far. The universe would have been opaque. Bright, hot, but visually shallow. The light would not have carried long-distance information because it could not travel long distances without being scrambled. So for a time, the universe was like a dense fog. Not a fog of water droplets, but a fog of charged particles. Light could not cross it cleanly. Then, as the universe expanded, something changed. Expansion is not only motion outward. It is also cooling. As the universe expands, its energy spreads out. Temperature drops. Conditions slowly shift from the extreme to the stable. At a certain point, the universe cooled enough for electrons to finally combine with nuclei to form neutral atoms. This moment is sometimes called recombination, not because it was a simple recombining of what we already know, but because it marks the transition from free charges to bound atoms. And once electrons were bound into atoms, they stopped scattering light so efficiently. The fog cleared. The universe became transparent. And in that moment, light was finally free to travel long distances in straight lines. The photons that existed then, released from the last time the universe was opaque, began their long journey outward. They have been traveling ever since. And they are still arriving now. This is the oldest light we can see. It is called the cosmic microwave background, the CMB, not because it is mysterious in name, but because of what happened to those photons over time. As the universe expanded, the wavelengths of that light stretched. What was once hotter, high-energy radiation has been shifted down into microwaves, too faint and too cold for human eyes, but detectable with sensitive instruments. So when we observe the cosmic microwave background, we are not just observing something very old. We are observing a boundary condition. We are observing the earliest time from which light can reach us directly. Anything earlier than that is hidden from ordinary electromagnetic observation, not because it did not exist, but because its light could not travel freely to form a clean image. This is a profound limitation. It means that the universe has a visible horizon. Not an edge in space, but an edge in time. A moment beyond which light cannot provide a direct window. And this is where the question of age becomes sharper. Because the CMB is not just an ancient signal. It is also a timestamp. It tells us, by this time, the universe had cooled enough to become transparent. By this time, certain physical conditions were in place. By this time, the universe had reached a stage where its history could begin to be read through traveling photons. So the CMB becomes one of the strongest anchors we have for the universe's early timeline. It provides a reference point. It is not the beginning of everything. It is the beginning of visibility. And that difference matters. Because many people hear oldest light we can see, and assume it means the moment the universe began. But it does not. It means the earliest moment from which light can carry information to us without being endlessly scattered. So the CMB is both a gift and a boundary. It gives us a direct look at the early universe in a way nothing else can. And it reminds us that even with perfect instruments, there are eras we cannot see with light. Yet within the CMB lies something even more astonishing. It is not perfectly uniform. If the early universe had been perfectly smooth, the CMB would be a featureless background, a single temperature, a single glow. But it contains slight variations. Tiny differences. The same kind of small differences we discussed earlier, the ones that later became everything. And in those tiny variations, the universe left us a map. A newborn portrait. A picture of its earliest structure seeds, still visible as faint patterns in microwaves across the sky. In the next chapter, we will look at that portrait more closely. Not as a technical graph, but as a story. A story of how minute imperfections in the oldest light became the scaffolding for galaxies, clusters, and the cosmic web, and how that helps us measure the age of the cosmos with surprising precision. When you first hear about the cosmic microwave background, it can sound like a single idea. Old light. A faint afterglow. A background glow left over from the early universe. But the most important thing about it is not simply that it exists. It is that it is not perfectly smooth. If the CMB were uniform, if it had exactly the same temperature and brightness in every direction, it would still tell us something, that the universe became transparent and light began traveling freely. But it would not tell us how the universe became structured. It would not explain why matter gathered into galaxies instead of remaining spread out forever. It would not contain the seeds of the cosmic web. Instead, it would be like an empty page. But the universe did not leave us an empty page. The CMB contains a pattern. So subtle that it is invisible to human senses. So small that it requires careful instruments and analysis to detect. And yet, in cosmology, that subtle pattern is one of the most precious records we have. Because those faint variations are not noise. They are memory. They are the early universe's unevenness frozen into light. In chapter 11, we talked about how small differences became everything. Here, we meet those differences directly, not as an abstract claim, but as something we can measure. The variations in the CMB are tiny temperature differences from one region of the sky to another. These differences are extremely small in magnitude, but they are real. And they matter because temperature in the early universe was tied to density. Slightly warmer regions correspond to slightly different conditions, regions that were, in effect, a little more or a little less dense than their surroundings. These were the beginnings of structure. Not galaxies yet. Not stars. Just a gentle texture in an almost uniform cosmic sea. But gravity does not ignore gentle texture. Gravity amplifies it over time. So what the CMB gives us is a snapshot of the universe before it had built the complex structures we see today, before filaments, before clusters, before mature galaxies. It shows us the universe at an early stage when the ingredients were present, but the outcomes had not yet emerged. And because the CMB is light from a known era, the era when the universe became transparent, it gives us a kind of calibrated photograph. A reference frame. A newborn portrait. This portrait does something remarkable. It allows us to connect today's universe to the early universe in a single continuous story. It allows us to say, with evidence, that the large-scale patterns of matter did not appear randomly. They grew from real, measurable early conditions. And that connection becomes one of the foundations for measuring cosmic age. Because once you have an early snapshot and a present snapshot, you can ask how much time had to pass for one to evolve into the other. Not in a simplistic way, as if you could watch it happen like a movie, but through models, careful, tested frameworks that describe how expansion, gravity, matter, radiation, and time interact. The CMB variations are so important because they contain multiple kinds of information at once. They tell us about the universe's early density fluctuations. They tell us about the geometry of space on large scales. They tell us about the mix of ingredients, how much ordinary matter there is, how much dark matter, how the expansion behaves. And when these pieces are combined, they give a consistent picture of how old the universe is and how it has evolved. But the documentary's tone is not to treat this as a finished triumph. Because there is a deeper lesson here about how science works at cosmic scales. We cannot touch the early universe. We cannot go there. We cannot recreate its full conditions in a laboratory. So we rely on fossil signals. And those signals must be interpreted with humility. We have to be careful not to mistake our models for reality. We have to remember that the CMB is not the whole early universe. It is the earliest surface we can see with light. It is the boundary of visibility. So it gives us an extraordinary window, but still only a window. And yet, within that window, the universe seems to be telling a coherent story. The early texture seen in the CMB is consistent with the later growth of structure. The present cosmic web, when simulated backward in time, tends to point toward a universe that began with tiny fluctuations like those. So the CMB becomes a bridge. It links the early smoothness to the later complexity. It turns the idea of cosmic history into something measurable rather than poetic. But there is another reason the CMB newborn portrait matters for our main question. It teaches us that seeing the past is not only about travel time. It is also about interpretation. The CMB arrives as microwaves from every direction, nearly uniform. To turn that into a map of early fluctuations, we had to learn how to measure and subtract foreground sources. Dust in our own galaxy, emissions from nearer objects, instrumental noise. We had to learn how to see through the clutter of the present in order to read the faint imprint of the past. So the universe's oldest visible signal becomes a lesson in method. The past is not simply there, waiting. The past must be extracted carefully from what arrives. And that brings us to the next step in our journey. Because the CMB gives us an early anchor, but most of the universe's visible story, galaxies, clusters, and structures, comes to us through different kinds of light. And to connect those observations to age, we need a method that turns the changing character of light into distance, and distance into time. One of the most essential tools for that is redshift. A subtle stretching of light that allows us to estimate how far away something is, and therefore how far back we are seeing it. In the next chapter, we will step from the newborn map into the practical craft of cosmology, how scientists translate light into time, and how a simple shift in color becomes one of the universe's most reliable clocks. If the cosmic microwave background is the universe's newborn portrait, then everything that comes after it, the era of galaxies, clusters, and large-scale structure, has to be reconstructed from the light those objects send us. And that brings us to a practical problem. A telescope can collect faint photons from a distant galaxy, but those photons arrive without a label. They do not announce their travel time. They do not carry a tag that says, "I left 8 billion years ago." So if distance becomes time, we still need a way to measure distance. Not by traveling, not by sending probes, but by reading the message itself. This is where one of the most quietly powerful ideas in cosmology appears. Redshift. At first, redshift can sound like a technical detail, a scientist's term for a small change in light. But in practice, redshift is one of the main bridges between what we observe and the history we are trying to understand. Because redshift is not merely about color. It is about the universe's expansion leaving an imprint on every traveling photon. To feel what redshift means, start with something familiar: waves. A sound wave has a pitch. That pitch depends on how close together the wave's peaks are. If the peaks are compressed, the sound is higher. If they are stretched apart, the sound is lower. Light behaves in a similar way, except the pitch of light is its color. Blue light has shorter wavelengths, peaks closer together. Red light has longer wavelengths, peaks farther apart. Now, in everyday life, there are two common ways wavelengths can change. One is motion. If a source is moving away from you, its waves stretch slightly as they reach you. This is the Doppler effect. It happens with sound and with light. But in cosmology, there is another stretching that matters even more. Space itself expands. And when space expands while light is traveling through it, the light's wavelength is stretched along with space. The photon keeps moving, but the distance between its wave peaks grows. So light that began as a certain color arrives with a slightly longer wavelength. Shifted toward red. This is redshift. And the reason it matters is that the amount of stretching contains information. The more the universe expanded during the light's journey, the more the light is redshifted. So redshift becomes a measure of how much cosmic history occurred while that photon was traveling. In simple terms, greater redshift usually means greater distance. Greater distance usually means greater look-back time. So redshift becomes a translator. It takes a property we can measure, the wavelength shift, and turns it into an estimate of distance, and therefore an estimate of when we are seeing the object. This is not perfect, and it comes with assumptions, but it is one of the most essential tools for mapping cosmic age. There is a quiet elegance to it. The universe expands. Light travels. The expansion stretches the light. And by measuring that stretch, we learn how deep into the past we are looking. So in practice, when astronomers observe a galaxy, they often look for known features in its spectrum, distinct patterns created by elements absorbing and emitting light at specific wavelengths. These features are like landmarks. If you know where the landmark should be in the spectrum, and you find it shifted, you can calculate how much it moved. That shift tells you the redshift. And the redshift tells you, approximately, how far away the galaxy is and how far back in time you are seeing it. This is why large-scale surveys of galaxies are so powerful. They do not only map where galaxies are on the sky. They map how far they are in time. By collecting the redshifts of thousands or millions of galaxies, astronomers create a three-dimensional map, 2 dimensions of direction, 1 dimension of distance, where distance is also history. This transforms the night sky into something like a time chart. Nearby galaxies appear as recent points. Distant galaxies appear as older points. Clusters and filaments appear not only as structures in space, but as structures evolving across time. And this is where the documentary story becomes more connected. Because now we can link multiple chapters together. We know the sky is delayed. We know the universe is structured. We know structure grows over time from small differences. We have a newborn map in the cosmic microwave background. And now we have a way to place galaxies into a timeline through redshift. But we also have to be honest about limitations. Redshift is powerful, but it is not a simple ruler you can apply without care. For nearby objects, redshift can be influenced by local motion, galaxies moving toward or away from each other within groups and clusters. At small distances, motion can blur the relationship between redshift and distance. At larger scales, the expansion dominates, and redshift becomes a stronger indicator of cosmic distance and time. But even then, converting redshift into a precise distance requires a model of how the universe expands, because the expansion rate can change over cosmic history. So redshift is not just a measurement. It is a measurement inside a framework. The framework must be consistent with other observations, like the cosmic microwave background and the growth of structure. This is why cosmology often feels like a conversation between evidence and model. We measure what we can. We build a model that explains it. We test the model against other measurements. We revise. We refine. The goal is not to force certainty. The goal is to build a story that remains coherent under pressure. In that sense, redshift does more than place galaxies on a timeline. It ties our idea of age directly to the behavior of the universe itself. Because redshift is, fundamentally, the expansion of space made visible in light. It is the universe's history written into the wavelength of the photons that cross it. And once you have redshift, you can begin to do something that earlier chapters only hinted at. You can begin to build a ladder of distance that reaches from nearby space to the deep universe. You can begin to place objects at different look-back times, and compare them, not as random samples, but as chapters in a continuous evolution. But to do that reliably, redshift alone is not enough. We also need foundational methods that anchor our distance measurements closer to home, where we can check and calibrate them, because you cannot map the far universe well if your near measurements are uncertain. So the next step is the quiet craft behind every large cosmic measurement. The distance ladder. A sequence of methods, each one reaching farther than the last, each one calibrated by what comes before. In the next chapter, we will explore how scientists build that ladder, how they measure distance step by step in a universe where direct measurement is rarely possible, and why our confidence in cosmic age depends on the strength of those links. Redshift gives us a powerful idea. The universe's expansion stretches light, and that stretching can be measured. With it, we can begin to place galaxies on a timeline. We can begin to translate far into long ago. But there is a quiet problem hiding underneath that power. To turn redshift into a distance, you need to know how the universe expands. And to know how the universe expands, you need reliable distances. So there is a loop in the logic. Distance helps define expansion, and expansion helps define distance. Science breaks loops like this by building anchors, measurements that do not depend on the thing they are trying to measure. This is where the distance ladder enters the story. It is called a ladder because no single method reaches across the entire universe. Space is too vast, and our tools are too specialized. Instead, we measure distance in steps, using different techniques for different ranges, and carefully connecting them so each step supports the next. The distance ladder is not one measurement. It is a chain of trust. And the strength of our understanding of cosmic age depends on how strong that chain is. The first rung is the simplest in principle, geometric distance. In our local neighborhood, we can measure distance directly through parallax, the apparent shift of a nearby star against the background as Earth moves around the Sun. It is the same logic your eyes use for depth perception, expanded to the scale of an orbit. Parallax is valuable because it is grounded. It does not rely on models of stars or galaxies. It relies on geometry. But parallax fades with distance. Stars become too far, the shift becomes too small. So the ladder climbs to the next rung. We then use standard candles, objects whose true brightness is known or can be inferred. If you know how bright something really is, and you measure how bright it appears, you can estimate how far away it must be. This sounds straightforward, but it requires careful identification. You have to be sure you are looking at the right kind of object, and you have to understand the relationship between its intrinsic brightness and what you observe. Certain variable stars are especially useful here. Their brightness changes in regular patterns, and those patterns are tied to their true luminosity. They become stepping stones to distances far beyond parallax. Then the ladder climbs again. For even larger distances, astronomers use explosions, supernovae, events so bright they can be seen across enormous stretches of space. Certain kinds of supernovae behave in ways that make their brightness predictable enough to serve as cosmological markers. These are not perfect rulers. They require calibration. They require correction. But when handled carefully, they allow us to reach deep into the universe, where redshift becomes a strong guide to distance and time. So the ladder is built like this. Close range, geometry. Mid-range, well-understood stellar indicators. Far range, powerful cosmic markers like supernovae. Deep range, redshift interpreted through an expansion model. Each rung depends on the ones below it. If the early rungs are wrong, the upper rungs wobble. And if the upper rungs wobble, our estimates of cosmic age wobble with them. This is why the distance ladder is not just technical background. It is the hidden backbone of nearly every claim we make about the universe's scale and history. It is also why cosmology is careful, even when it sounds confident. Because the universe is not kind enough to offer a tape measure. It forces us to build one. And building one across billions of light years requires patience and cross-checks. Astronomers do not rely on one method alone. They compare methods. They look for consistency. They test whether different distance indicators agree when applied to the same region of space. Where they agree, confidence grows. Where they disagree, something important may be happening. Sometimes the disagreement is in the data. Sometimes it is in the calibration. Sometimes it is in the assumptions. And sometimes, quietly, rarely, it hints that our model of the universe might be incomplete. This is part of why the question of cosmic age remains so compelling. Because age is not simply a number we announce. It is the outcome of a carefully constructed measurement system. And in that system, uncertainty is not a weakness. It is information. The distance ladder also teaches us something about how knowledge works at cosmic scales. We do not begin by trying to measure the entire universe. We begin by measuring what is close enough to test. We build outward. We extend our reach carefully, step by step, making sure the chain remains coherent. In a sense, cosmology mirrors human learning. We begin with what we can touch, then we build abstractions that reach beyond touch, anchored by what we have verified. And now, with redshift and the distance ladder in place, we have the tools to do something crucial for our main journey. We can begin to connect the universe's structure to its expansion. We can begin to ask, if the universe expands, how does that expansion change over time? Because the age of the universe is not only about how far back we can see. It is about how the universe has been unfolding, how quickly it expanded, how its rate may have changed, and what that implies for the time elapsed since the early dense state. So the next step is to connect distance measurements to the universe's expansion history. To treat expansion not as a vague idea, but as a measurable behavior that can be turned into a timeline. In the next chapter, we will explore how expansion becomes the shape of the story itself, how time, distance, and the universe's growth are woven together into one continuous narrative. By now, we have built the tools that allow the universe to become measurable in time. We have the idea of light travel delay, distance becoming a clock. We have redshift, expansion written into light. We have the distance ladder, our chain of trust that lets us place objects at meaningful distances. Now we can approach the larger structure underneath all of this. Because the age of the cosmos is not only a matter of how long light has been traveling. It is a matter of how the universe itself has been changing while that light traveled. And the most important large-scale change is expansion. The universe expands. This statement is familiar, but it is often misunderstood. Many people imagine expansion as an explosion, as if everything began at a center and flew outward into empty space. That picture feels intuitive, but it is not what cosmology means. Expansion, in the cosmological sense, is closer to this. Space itself is stretching. The distances between galaxies, on average, increase over time, not because galaxies are racing through space away from a central point, but because the space between them is growing. This is not a claim about local motion. Galaxies inside a cluster can orbit each other. Stars inside a galaxy can remain bound. Gravity can hold structures together. Expansion is the large-scale behavior of the universe, visible when you average over enormous distances. So if space stretches, then the universe has a kind of scale factor, a way to describe how big the universe is at one time compared to another. And if the universe has been stretching, then earlier it was smaller, denser, hotter. This is the foundation of cosmic age. Because the age of the universe is, in practice, the time elapsed since the universe was in that earlier, denser state. But to go from it expands to it is this old, we need to understand something subtle. Expansion is not necessarily constant. The universe does not have to expand at the same rate forever. In fact, it would be surprising if it did. The contents of the universe matter. Matter pulls through gravity, tending to slow expansion. Radiation behaves differently, dominating early conditions. And later, another influence appears, something that behaves like a pressure pushing the expansion faster. So the expansion history, the way expansion changes over time, is the shape of the story. If you know the expansion history, you can estimate how long it has taken for the universe to go from a small early state to the large present one. That time is the age. Think of it like this. If you know how fast a river is flowing at different points, you can estimate how long it takes to travel from the source to where you are standing. If the river speeds up and slows down along the way, the travel time depends on the whole path, not just one measurement. Cosmic age is similar. We observe the universe now. We see its expansion now. We also gather evidence of how expansion behaved in the past. And from that, we infer the total elapsed time. This is where redshift becomes more than a distance tool. Because redshift is not just how far. It is how much the universe expanded while the light traveled. So if we measure redshifts and distances of many objects, we can begin to trace expansion as a function of time. We can ask, at a given redshift, meaning at a given look-back time, how fast was the universe expanding? How were distances changing? And then we can integrate that story into a timeline. But the documentary tone here is not to turn into math. The point is conceptual. The age of the universe is not a single measurement taken at one place. It is the outcome of connecting many observations into one consistent narrative of expansion. And that narrative must agree with the evidence we already have. It must agree with the cosmic microwave background, which encodes early conditions. It must agree with the growth of structure, which depends on how matter had time to gather. It must agree with distances measured by the ladder, which ground redshift into actual scale. So expansion becomes the spine that holds the story together. Without it, age is just a word. With it, age becomes a calculable property of a coherent model. And yet, there is something almost unsettling about this. Because expansion is not a local experience. You do not feel it in your body. You do not see your room stretching. You do not watch your city drift away. Gravity and forces bind local systems, and the effects of expansion at human scales are unimaginably tiny. So the universe's most important large-scale behavior is something we know primarily through inference. Through patterns in light. Through the systematic redshift of distant galaxies. Through the statistics of structure. So again, the story returns to the same theme. We do not know the universe by direct contact. We know it by reading messages. And those messages have to be arranged into a consistent shape. Now, when cosmologists talk about expansion, They often use a parameter that captures the present expansion rate, how quickly the universe is expanding today. Measuring this rate is one of the central projects in modern cosmology because it strongly influences the inferred age. A faster present expansion rate, all else equal, can imply a younger universe. A slower rate can imply an older one. But all else equal rarely holds. Because the expansion rate changes over time, and the contents of the universe determine how it changes. So to truly understand age, we need to know not only that the universe expands, but how expansion behaves across cosmic history. This is why the age of the universe is not an isolated curiosity. It is tightly connected to the universe's composition, to matter, to radiation, to whatever is driving acceleration. And this is why disagreements about expansion measurements are so important. They ripple directly into the story of age. But before we reach those modern tensions, we need to honor the moment when expansion first became part of science. Because there was a time when the universe was assumed to be static, eternal, unchanging, fixed in place. And then a discovery changed everything. Not in the sense of a sudden emotional revelation, but in the sense of a quiet, irreversible shift. The universe was found to be expanding. That turning point is the next chapter. In the next chapter, we will follow the historical moment when expansion was discovered, and see how a small pattern in light became evidence that the universe has a past, the universe did not feel like something that could have an age. It felt eternal. The sky changed through the night, the seasons shifted, but the stars themselves seemed fixed, steady points that belonged to a permanent background. Even when people imagined the cosmos as vast, they often imagined it as timeless. And in the early days of modern science, that assumption lingered. A static universe felt natural. Not because it was proven, but because it matched the quiet appearance of the sky. Then, slowly, that appearance began to break. Not through philosophy, not through speculation, but through careful observation, through light measured with enough precision that its subtle patterns became evidence. The turning point was not a single dramatic moment. It was a convergence, better telescopes, better spectroscopy, better cataloging of faint objects, and a growing realization that many of the nebulae in the sky were not clouds inside our own galaxy, but galaxies in their own right, island universes, unimaginably far away. Once galaxies were understood as separate systems, the question of their motion became meaningful. Were these galaxies stationary? Were they moving? And if they were moving, how? The key was hidden in their light. When astronomers spread a galaxy's light into a spectrum, they found recognizable features, lines associated with known elements. Those lines acted like landmarks. In the laboratory, the positions of those lines were well established. But in many galaxies, those landmarks were shifted. Not by a little. By a consistent pattern. The lines were moved toward the red end of the spectrum. Redshift. At first, redshift could be interpreted as motion. A galaxy moving away would show its light stretched, similar to the Doppler effect. This idea already existed, but the scale of what was being observed was something new. Because the redshifts were not random. They were systematic. And then another pattern emerged. The more distant the galaxy, the greater the redshift tended to be. This was the quiet clue that changed cosmology. Distance and redshift were linked. Which meant distance and recession were linked. Which meant the universe, at large scales, was not static. It was expanding. This was not merely a new fact. It was a new framework for what the universe is. A static universe has no natural earlier state in the same sense. It can be imagined as eternal, always roughly as it is. But an expanding universe implies that the past was different. If the universe is larger now, it was smaller before. If it was smaller before, it was denser before. If it was denser before, it was hotter before. And suddenly, the idea of cosmic history becomes inevitable. Not as mythology. As physics. Once expansion is real, the universe becomes a process. And once the universe becomes a process, it becomes something that can have an age. This is why the discovery of expansion is the central turning point in the entire story of cosmic time. It turns the question, how old is the universe, from philosophical curiosity into scientific measurement. Because if expansion has been happening, you can, in principle, trace it backward. Not to an exact moment you can photograph, but to an earlier era when conditions were extreme. And you can estimate how long it has taken for expansion to bring the universe to its current state. This becomes the age. But the turning point also introduced a new kind of humility. Because the discovery was not made by someone seeing expansion directly. No one watched galaxies move away through a cosmic time-lapse. It was inferred from light. from subtle shifts measured carefully in spectral lines. So even at the moment the universe's biggest behavior was revealed, it was revealed through the same method we've been building toward all along. Receiving delayed messages, interpreting them, constructing a coherent picture, and from that picture, discovering that the universe is not timeless. It has a past. It has a direction. It has a history. This turning point also rearranged the meaning of our place in the cosmos. If the universe expands, then distances grow. Light from distant galaxies is stretched. The farther you look, the earlier you see. And the early universe begins to come into view not as speculation, but as an accessible domain, accessible through the time delay built into light itself. So the discovery of expansion is not only a discovery about motion. It is a discovery about the structure of time in the universe. It establishes that cosmic time is not just our time projected outward. Cosmic time is woven into space itself, into the way distances change. And now, with expansion as the backbone, cosmology becomes a science of reconstruction. We ask, what expansion history best fits all the evidence? What expansion history matches the oldest light, the cosmic microwave background? What expansion history matches the growth of the cosmic web? What expansion history matches the distances we measure through standard candles? When those pieces fit together, the universe's age becomes something we can estimate with confidence. But the story did not end with the discovery that expansion exists. Because once scientists began to measure expansion more precisely, they found something unexpected. They expected expansion to slow down. Matter has gravity. Gravity pulls. Intuitively, you might expect the universe's expansion to be gradually decelerating. For a long time, that was the assumption. Then evidence arrived suggesting something else. Not a gentle slowing. A subtle speeding up. An accelerating expansion. And that discovery did not just adjust the details. It altered the entire shape of the universe's history, and with it, the way we calculate age. That is where we go next. In the next chapter, we will explore the surprise of accelerating
Once the universe
expansion
was understood
and
to
how
be
it introduced a new unknown
natural
into the heart of
expectation
cosmology. A
If
force-like
matter fills
influence
space
that seems to
and
push
matter has
space
gravity,
apart,
then
shaping
gravity
the
should
universe's
pull back.
past and its long
Not
future.
enough
to stop expansion everywhere, perhaps, but enough to slow it down over time. This expectation felt calm and reasonable. It fit the idea of gravity as a universal influence, always attractive, always gathering, always resisting separation. So for decades, the question was not whether expansion existed, but how it was changing. Was it slowing slightly? Was it slowing strongly? Would it eventually stop? Would the universe recollapse? These were serious possibilities. And to answer them, astronomers needed a way to measure the expansion rate across time, not only now, but in the past. This is where one of the most important observational strategies in modern cosmology comes in. If you can measure distances to very distant galaxies, far enough that you are looking billions of years back, then you can compare how bright they appear to how redshifted they are. In other words, you can compare distance indicators to the stretching of space. This comparison is subtle, but it has power. Because it tells you whether the universe's expansion has been slowing or speeding up over the time that light has been traveling. For a long time, the expectation was deceleration. Then, when the data became strong enough, it suggested something else. A universe that was not only expanding, but expanding in a way that, over recent cosmic history, appears to be accelerating. This was the surprise. Not because it was emotionally shocking, but because it violated the simplest gravitational intuition. If gravity attracts, why would expansion speed up? The calm answer is that something else must be influencing the large-scale behavior of space. Something that behaves like a kind of repulsion, or more precisely, like a negative pressure, an effect that, on cosmic scales, causes space to expand faster. We call this influence dark energy. But the name does not solve the mystery. It is a label, not an explanation. And it marks one of the most quietly unsettling truths in modern cosmology. The dominant factor shaping the universe's large-scale expansion may be something we do not understand. Dark energy matters because it changes the universe's timeline. If expansion is accelerating now, it means the expansion rate has changed over time. It means the universe's history is not a simple smooth slowdown from a fast beginning to a slow present. Instead, the story has phases. An early phase when radiation and matter dominated. A long phase when matter-shaped structure growth. And a later phase when dark energy becomes important, pushing expansion to accelerate. These phases affect how we estimate the age of the universe, because age depends on the entire expansion history, not just the expansion rate today. Think of the universe's expansion like a long journey. If you travel from one city to another and your speed changes along the way, fast at first, slow in the middle, faster later, you cannot estimate the travel time accurately by looking only at your speed at the end. You need the whole speed profile. Cosmic age is similar. To estimate how long it has been since the early dense state, we need to know how the expansion rate changed across cosmic time. So the discovery of acceleration did more than add a new ingredient. It reshaped the curve of the universe's past. It forced cosmology to update its timeline, to include a component that affects the stretching of space itself. It also introduced a new kind of tension into the story. Because dark energy is inferred. It is not observed as a glowing thing. It is not detected as particles in a laboratory. It is deduced from the behavior of expansion. From a mismatch between what matter-only gravity would predict and what the universe seems to do. So again, the theme repeats. We learn the universe through traces. We infer the invisible from patterns. And we accept that our knowledge is constructed, not invented, but assembled from evidence that arrives late and incomplete. This matters for another reason. Acceleration affects the future. A universe that accelerates will carry distant galaxies away faster and faster over time. Regions of the universe will drift beyond our horizon, not because they vanish, but because their light will no longer be able to reach us as expansion outpaces the travel. So dark energy is not only a factor in calculating age. It is a factor in defining what can ever be observed. It shapes the boundary of visibility. It shapes the ultimate limits of knowledge. But before we reach those far horizons, we return to something closer. Because the universe's expansion history is not only expressed in numbers and models. It is also expressed in the growth of structure, the cosmic web, clusters, filaments, and voids. Matter has been gathering under gravity while space has been expanding. Those two processes, gathering and stretching, compete and collaborate across time. So to continue our single continuous journey, we now return to the universe's architecture, but with new understanding. We will look at the cosmic web again, this time not only as a pattern, but as a record of an expanding, evolving cosmos whose age is written into its structure. In the next chapter, we will enter the cosmic web on its largest scales. If you could step far enough away from the Milky Way, over billions of years, individual galaxies no longer dominate your skeleton, you would begin to see something that looks less like a scattered universe and more like a connected one. Not connected by wires or paths, but connected by gravity. A pattern of gathering. A slow geometry of matter. This is the cosmic web. It is one of the best reminders that the universe is not only expanding. It is also building. While space stretches, matter clumps. While distances grow, gravity pulls. And over billions of years, the result is an architecture that is neither uniform nor random. Long filaments. Dense nodes. Great walls of galaxies. And enormous voids, regions so empty that nothing begins to feel like a physical feature. The cosmic web matters in a documentary about age because it is a record of time written into shape. The web did not appear fully formed. It had to grow. Early on, the universe was closer to smooth. Those tiny differences in density we met in the cosmic microwave background, the newborn texture, were the beginning. But at first, they were only hints. Barely uneven. Then gravity began its slow work. Denser regions pulled in matter. Slightly emptier regions became emptier as matter flowed away from them. The contrast increased. The web sharpened. And as the universe aged, the pattern became more pronounced. So when we look at the cosmic web today, we are not only mapping where galaxies happen to be. We are looking at the outcome of billions of years of evolution. And this is crucial, because the cosmic web gives us a second way to read time that does not depend only on light travel delay. Light travel delay tells us when the message left. Structure tells us how much time has passed for matter to organize into what we see. In other words, the cosmic web is a clock made of maturity. A young universe has less developed structure. An older universe has more. And because we can observe the universe at different distances, and therefore at different look-back times, we can compare structure across eras. We can look at nearby space, where the web is mature. We can look deeper, where the universe is younger, and see whether the web is less developed. We can watch, indirectly, the growth of cosmic architecture across time. This is one of the most beautiful forms of evidence in cosmology. The universe lets us observe its own history by looking outward. But to do this, scientists needed more than a few images. They needed surveys. Massive catalogs of galaxies mapped across large regions of the sky, with distances inferred through redshift, producing 3D maps where the third dimension is time. When those maps were created, the web emerged clearly. Galaxies were not sprinkled evenly. They were arranged along filaments. Clusters appeared like knots where filaments meet. Voids opened like caverns between them. This is not only visually striking. It is physically informative. Because the cosmic web depends on the ingredients of the universe. Change the amount of matter. Change the behavior of dark matter. Change the expansion history. Change the influence of dark energy. And the web's growth changes. So the cosmic web becomes a test of our cosmic story. If our model of the universe is correct, then simulated universes built from that model should grow webs similar to the one we observe. And remarkably, when scientists include the main ingredients, ordinary matter, dark matter, expansion, and a dark energy-like component, simulations can reproduce web-like structures that resemble reality. This does not mean we have solved everything. But it means our story has internal consistency. And internal consistency is what allows an age to become meaningful. Because age is not just a number you announce. It is the amount of time required for the universe, under its known rules, to evolve from early conditions into the structures we see. So when we talk about the age of the cosmos, we are also asking, has there been enough time for the cosmic web to form? Has there been enough time for clusters to assemble? Has there been enough time for galaxies to mature? These are not philosophical questions. They are constraints. They are ways the universe checks our work. But the cosmic web also carries a quieter message. It reminds us that most of the universe is not made of the things we are most comfortable imagining. The glowing filaments we see are traced by galaxies, but galaxies are only the luminous highlights. Much of the mass shaping the filaments is dark. Much of the web is built by invisible scaffolding. So the universe's largest structures are built from something we do not directly see. And yet we still map them. Not by guessing, but by collecting signals and interpreting their patterns. This creates a particular mood, one that fits the tone of our documentary. A calm awe. Because the universe is knowable, but not fully. It reveals itself in outlines, in shadows, in indirect readings. And when we map the cosmic web, we are mapping a shadow of a deeper structure. Now, at this stage of the journey, we have reached large scales. But the story still needs to progress logically. We have seen how early differences grow into structure. We have seen how the web forms. We have connected age to expansion history. The next question is inevitable. If the web is the mature architecture, then what was the first time the universe produced light sources within that architecture? When did darkness first break? When did the first stars form? Because stars are not just objects, they are turning points. They create heavier elements. They transform gas. They begin the long chemical story that eventually leads to planets, to complexity, to life. So to continue our unified journey, we now move from the web's large-scale skeleton to the first lights that appeared within it. In the next chapter, we will step into the era when the universe began to ignite, when the first stars formed and the cosmic dark slowly started to change into a universe that could be seen. There is a long stretch of the universe's history that is easy to forget, because we have no direct memory of it in the night sky. We look up and see stars everywhere, as if starlight has always been the universe's natural condition. But it wasn't. There was a time after the universe became transparent, after the oldest light we can see began its journey, when there were still no stars. No galaxies. No bright points. Just expanding space, cooling gas, and gravity beginning its slow work. In that era, the universe was dark in a very specific way. Not because light did not exist, but because there were no concentrated sources of visible light, no luminous objects shaping the sky. This period is sometimes called the Cosmic Dark Ages. The name can sound dramatic, but the reality is quieter. It was simply the time when the universe contained matter that had not yet condensed into stars. And the transition out of that darkness, the first ignition of starlight, is one of the great turning points in cosmic history. Because stars do not merely shine, they transform. They are engines of chemistry and structure. They take simple ingredients, mostly hydrogen and helium, and begin turning them into heavier elements. They heat their surroundings. They flood space with radiation. They reshape gas clouds. Over time, they make possible everything that later becomes complex. So if we are asking about the age of what we see, the first stars matter because they mark the moment when the universe began to produce the kinds of visible signals that dominate our astronomy. But how do we talk about the first stars when we cannot simply point a telescope at them and watch them form? We return again to the documentary's central method. We reconstruct. The first stars were likely different from most stars that exist today. Not because the laws of physics were different, but because the conditions were different. There were no heavy elements yet, no carbon, no oxygen, no silicon, no iron in the amounts we see now. The gas was simpler. Cooling processes were different. The pathways by which clouds collapse were not the same as they are in a chemically enriched universe. So the earliest stars may have been unusually massive, bright, and short-lived, stars that burned fast and died young, leaving behind seeds for later generations. This is not a certainty. It is a careful inference based on what the early universe was made of and what kinds of cooling and collapse are possible with those ingredients. And whether the first stars were extremely massive or merely somewhat different, the core point remains. They began the universe's luminous era. They began the long chain of enrichment that made later stars, planets, and chemistry possible. They also began changing the universe's transparency again. Because the first stars emitted intense ultraviolet light. That light interacted with the surrounding hydrogen gas. Over time, it helped reionize the universe, turning neutral hydrogen back into ionized plasma in vast regions of space. This was another transformation of the cosmic medium. The universe went from opaque, early plasma, to transparent, neutral atoms, and then, over time, became more ionized again due to starlight and galaxy formation, but now in a universe that remained largely transparent on large scales. So the first stars did not simply add light. They changed the environment. They created an era in which the universe's chemistry, temperature, and visibility evolved together. And this is where the story of age becomes richer. Because the age of the cosmos is not just how long it has been expanding. It is how long it has been producing complexity. The first stars are one of the earliest milestones in that complexity. So the question becomes, when did they form? Not as a single date, but as an era. An interval in cosmic time when darkness began to give way to light. Astronomers infer this through several lines of evidence. They study deep-sky galaxies at high redshift, galaxies so far away that their light comes from an early universe. They look for signs of early star formation and how rapidly it was happening. They study the cosmic microwave background for subtle imprints caused by the reionization process, which affects how CMB photons scatter. They examine the absorption features in the light of distant quasars, bright beacons whose light passes through intervening gas, revealing how much neutral hydrogen existed at different times. None of these is a direct movie of first stars forming. But together they create a timeline. A range where the universe transitions from a mostly dark, neutral state into one filled with the first luminous sources. And within that range, our models and observations can be compared. This chapter is important because it sets up the next major step. Stars are not isolated forever. Once you have stars, gravity begins to gather them into larger systems. Small early galaxies form. They merge. They grow. They become the building blocks of the mature galaxies we see nearby, including the Milky Way. So after the first stars, the next great story is the first galaxies. Not the large, well-ordered galaxies we see in the modern universe, but early galaxies that were smaller, more chaotic, rapidly forming, and difficult to observe, because they exist at extreme look-back times and are often faint. The age question becomes sharper here. When we observe the earliest galaxies we can detect, we are not just seeing objects far away. We are witnessing the universe learning how to build structure that shines. And that tells us something about how quickly complexity emerged after the beginning, how fast the universe moved from smoothness to stars, from stars to galaxies, from galaxies to the web. In the next chapter we will enter that era. We will look at the first galaxies, small, strange, hard to see, and explore what their existence reveals about the universe's age, its growth, and the limits of our ability to observe the earliest chapters of cosmic history. Once the first stars began to ignite, the universe crossed a threshold. It was no longer only cooling and expanding. It was also building luminous structure. But stars alone do not create the kind of universe we recognize. A universe filled with isolated first stars would still be mostly dark, mostly empty, with light scattered thinly across space. What makes the cosmos visually and physically rich is organization. Stars gathering into systems. Systems gathering into larger systems. Gravity turning scattered matter into something with shape. That next step is the first galaxies. And the first galaxies matter not only because they are beautiful. They matter because they are historical evidence. They tell us how quickly the universe learned to build complexity after the early, nearly uniform era. They show us how far back we can trace the growth of structure. And they force us to face the limits of what observation can do, because these objects exist at extreme distances, so far that the light we receive from them comes from a universe that was still young. The first galaxies were almost certainly not like the calm spiral forms we picture today. They were likely smaller, less orderly, more irregular, more violent in their internal activity. This is not a matter of imagination, it follows naturally from what it means for a galaxy to be early. Early galaxies are still assembling. They are still gathering gas. They are still merging with neighbors. Their stars are forming rapidly. Their shapes have not had time to settle into stable patterns. So when we try to observe them, we should not expect them to look like the familiar Milky Way. We should expect something more raw. A galaxy in its earliest stages is a system in motion, not an object at rest. And yet observing these early systems is one of the most difficult tasks in astronomy. For two reasons that are easy to state but hard to fully feel. First, distance makes them faint. Light spreads as it travels. The farther it goes, the more it thins. Even if an early galaxy is forming stars intensely, its light has to cross billions of light-years to reach us. Second, the universe's expansion changes the light. As the light travels, its wavelength stretches. What begins as ultraviolet or visible light arrives shifted into the infrared. So the earliest galaxies are often not best seen in the same wavelengths that our eyes detect. This means we need instruments sensitive to faint infrared light, able to separate it from nearer sources and background noise. So the first galaxies sit at the edge of our practical vision. They are there, but they are difficult. They are real, but they are subtle. And that subtlety introduces a crucial theme for our documentary. Early history is not only distant. It is fragile. The deeper we look, the more the universe's signals become weak, stretched, and hard to interpret. So the first galaxies are not just scientific objects. They are tests of method. They force us to ask, when we see a faint patch of light at extreme redshift, what are we truly seeing? Are we seeing a mature galaxy? A small cluster of star-forming regions? A merger in progress? A temporary burst of activity? And how do we avoid mistaking our models for certainty? This is where cosmology becomes careful again. Because early galaxies are not simply found like a planet in our neighborhood. They are inferred, confirmed, cross-checked. Spectra are measured when possible. Redshifts are estimated. Photometric methods are used when light is too faint for full spectra. Multiple observations are compared. And even then, conclusions remain provisional until evidence becomes stronger. This is not weakness. It is the honest posture of a science working at the limits of what can be observed. But despite these difficulties, the existence of early galaxies is one of the clearest signs that the universe's structure grew relatively quickly in cosmic terms. Not quickly in human terms. Nothing about billions of years is quick to us, but quickly compared to the universe's total timeline. Because if we can see galaxies already forming at high redshift, it means that the early density fluctuations had time to grow, gas had time to collapse, stars had time to ignite, and systems had time to gather into luminous structures. So the first galaxies become milestones in the age story. They tell us that by the time their light left them, the universe had already passed through multiple phases. Becoming transparent. Beginning structure growth. Forming first stars. And then assembling the first galaxies. That sequence implies a timeline. And the timeline can be compared to what expansion models predict. If the models say the universe was too young for galaxies to exist at a certain redshift, but we observe them anyway, then the models must adjust. If the models predict galaxies should be there, and we see them, confidence grows. So early galaxies are both evidence and constraint. They guide the cosmic story and test its consistency. There is another subtle point here, one that connects back to our original question about the age of everything we see. When you look at an early galaxy, you are looking at more than an object. You are looking at an era. You are witnessing a universe that had not yet become the one we inhabit today. The cosmic web was less mature. Clusters were less developed. The chemical elements were fewer. The background conditions were different. So the first galaxies are like living fossils, not fossils in the sense of dead remains, but in the sense that they preserve early conditions in their light. And that preservation is part of what makes deep observation so valuable. It lets us compare different eras directly. It lets us ask how galaxies change as the universe ages. And as we move forward in our documentary, we will see that the story of age is not only about the far universe. It is also about finding ancient evidence close to home, because sometimes the oldest things are not far away. They are nearby survivors. Old stars in our own galaxy. Ancient globular clusters. Chemical fingerprints that preserve early conditions. So after we explore early galaxies, we will eventually return to the local universe and ask, Can we find ancient objects here that help us calibrate cosmic time from the inside? But before we return home, we have one more step outward. Because early galaxies do not exist alone. They gather, merge, and grow into larger systems. And those systems connect to the biggest question of structure and age, how the universe builds from small early patches into vast clusters and walls. So the next step is to understand how we can date what we see, not only by distance, but by interpreting the development stage of objects and structures. We need to understand what kinds of evidence allow us to say, with care, that something is older or younger, not just in how long its light traveled, but in its intrinsic history. To do that, we will begin to shift our approach. We will start looking for the oldest things nearby, cosmic fossils in the Milky Way, because those fossils give us a different route to age, one that complements deep space observation. In the next chapter, we will return toward home, and meet the ancient stars that still orbit within our galaxy, survivors from early cosmic eras, whose chemistry and life stages allow us to infer time in a way distance alone cannot. Up to this point, the journey has mostly moved outward. Outward into distance. Outward into earlier light. Outward into a younger universe seen through old signals. This outward movement is powerful because it makes time visible. The farther we look, the earlier we see. Deep space becomes a natural archive. But it can also create a subtle illusion. It can make us believe that the only way to study the early universe is to look far away. That is not entirely true. Because some of the universe's oldest evidence is not at the edge of observation. Some of it is nearby. Some of it is orbiting quietly inside the Milky Way. Ancient stars. Survivors. Not ancient because their light took a long time to reach us. Many are close enough that their light is nearly recent compared to cosmic scales. They are ancient because the stars themselves have existed for an extraordinarily long time. They formed early in the universe's history and they are still here. So in this chapter, the documentary makes an important shift in method. We are no longer relying only on look-back time. We are doing something closer to archaeology. We are asking, can we find objects that formed long ago and remained intact long enough to carry that history into the present? Because if we can, then the age story does not depend only on distance. It can also be read locally, through the properties of ancient survivors. This is one of the most calming and also most profound ideas in cosmology. The early universe is not completely lost. It is still present in fossils. Not fossils of bone and stone, but fossils of starlight and chemistry. A star is not merely a glowing ball of gas. It is a chemical record. When a star forms, it forms from the gas available in its environment. That gas contains certain elements in certain proportions. And the star's composition reflects that. This is why astronomers often speak of metallicity, a term that can be confusing because it does not mean metal in the everyday sense. In astronomy, metals means any element heavier than hydrogen and helium. In the early universe, there were almost no heavy elements. The universe began mostly with hydrogen and helium, with tiny traces of a few light elements. The heavier elements, carbon, oxygen, silicon, iron, were manufactured later inside stars and spread outward through stellar winds and explosions. So the earliest generations of stars formed in a universe with very few heavy elements. They formed from simpler gas. And that simplicity is preserved as a chemical fingerprint. If you find a star with extremely low metallicity, you are likely looking at a star that formed early, before the universe had been enriched by many generations of stellar death. So ancient stars become time markers. Not because they tell you the age of the universe directly, but because they tell you that certain eras existed, and they allow you to estimate how long ago those eras were. They also allow you to build a consistency check. If the universe has a certain age, then there should be stars old enough to approach that age, but not older. If you ever found a star confidently older than the universe, it would be a problem so deep it would force a major revision. In practice, the search for the oldest stars has helped tighten our understanding of cosmic age, not by contradiction, but by agreement and constraint. So where do ancient stars live? Many of them are found in places that match the idea of survival. Some live in the halo of the Milky Way, an extended region around the galaxy's disk, containing older stellar populations and globular clusters. Globular clusters are especially important here. They are dense, spherical collections of stars, often very old, orbiting in the halo. They formed early and have remained gravitationally bound for billions of years. When you look at a globular cluster through a telescope, you are not only seeing a beautiful concentration of light. You are seeing a community of stars that has been aging together since the early universe. These clusters become laboratories for time. Because inside them, stars of many masses evolve at different rates. Over billions of years, the more massive stars leave the main sequence, change shape, die. The less massive stars persist. So the cluster's population becomes a map of stellar aging, and by comparing that population to models of stellar evolution, astronomers can estimate the cluster's age. Again, not with perfect precision but with careful inference. And those ages, often extremely old, give us one of the most grounded forms of cosmic time measurement. This is what makes this chapter so important to the documentary's flow. We are connecting the far universe and the near universe into one continuous story. Deep space shows us the universe in earlier stages. Local fossils show us early-era objects that survived into the present. Together, they create a stronger timeline than either could alone. They also deepen the emotional tone in a calm way, because there is something quietly moving about the idea that ancient stars still exist near us. The universe does not discard all its early chapters. Some remain, faint but enduring, orbiting above the bright disk of the Milky Way, carrying chemical signatures of a time when the universe was simpler. This also changes how we interpret age when we look at the sky. It reminds us again that there are multiple clocks. The travel time of light tells you when you are seeing something. The age of stars tells you how long something has existed. The chemical fingerprint tells you what kind of universe existed when it formed. So age becomes layered. And layered age becomes something we can reconstruct more reliably. But now we have reached a natural next step. If ancient stars and clusters can be used as fossils, we need to understand how scientists actually date them. Not by watching them for billions of years. Not by guessing. But by using physical models that connect observable properties, brightness, color, temperature, composition, to a star's life stage and therefore its age. So the next chapter is about method. How we date stars without watching them age. How we turn a star's position on a diagram into a timeline. How we handle uncertainty without losing coherence. Because if we can date stars and clusters well, we gain one of the strongest independent supports for the universe's age story. In the next chapter, we will explore the craft of stellar dating, quiet, careful, and foundational, and see why the ages of nearby ancient stars are essential to understanding the age of everything we see. The universe does not give us the kind of time evidence we are used to. On Earth, we can date a tree by counting rings. We can date a stone layer by looking at what sits above it and below it. We can study growth and decay because we can observe change on human timescales. But stars do not change for us in that way. A star's life is long. Even the short-lived stars live far longer than a human life. The slow ones, small, steady stars, can persist for spans that dwarf the history of life on Earth. So if we want to know a star's age, we cannot simply watch it. We cannot wait. We have to infer. And inference in astronomy is not guesswork. It is pattern recognition grounded in physics. Stars are not random objects. They are governed by structure. Gravity pulling inward, pressure pushing outward, nuclear fusion releasing energy, and the flow of that energy toward the surface. A star's mass, how much matter it contains, is the main factor shaping its entire life. Mass determines how hot the core becomes, how fast fuel is consumed, how bright the star shines, and how quickly it moves through different stages of existence. So the secret of stellar dating begins with a quiet idea. Stars age in predictable ways. Not predictable in every detail, but predictable enough that a star's observable properties, its color, brightness, temperature, spectrum, can be linked to where it sits in its life cycle. This is the foundation. We date stars not by timekeeping but by life stage. To do that, astronomers use one of the most important tools in stellar astronomy. A diagram that sounds technical but represents a simple idea. Plot stars by brightness and by color. Brightness tells you how much light a star emits. Color tells you something about temperature. When you do this for a population of stars, especially stars that formed around the same time, you see patterns emerge. The stars do not scatter randomly. They occupy regions that correspond to different phases of stellar life. This is not coincidence. It is physics. Now, if you take a globular cluster, an ancient collection of stars that formed roughly together, you have something extremely valuable. A group of stars that share a common origin but have different masses. The heavier stars evolve faster. The lighter stars evolve slower. So in the clusters diagram, you can see which stars have already left the long stable phase of fusion and begun changing into later stages. And there is one particular feature that becomes the cluster's clock. The point where stars begin to peel away from the main sequence, the turn-off point. This is where stars of a certain mass have exhausted the hydrogen fuel in their cores and begin to evolve into a different state. The higher the mass, the faster this happens. So if you find the mass corresponding to that turnoff, you can infer how long the cluster has been aging. This is one of the calm triumphs of astrophysics. A population pattern becomes a timeline. But a documentary in this style must keep the tone honest. This method is powerful, but it is not perfect. Because to translate a turnoff point into an age, you need models of stellar evolution. Those models must account for composition, rotation, internal mixing, and other factors. And composition matters because stars formed early in the universe have different chemical environments than stars formed later. So dating a star is not simply reading a dial. It is comparing observation to a well-tested physical story. That story has uncertainty. So astronomers handle this in two ways: calibration and cross-checking. Calibration means using stars whose distances and properties we can measure reliably, especially nearby stars, so that the relationship between brightness, color, and intrinsic properties is grounded. Cross-checking means using different dating methods and seeing whether they agree. Because stars can sometimes be dated not only through cluster population patterns, but also through stellar composition. Very low metallicity suggests early formation, not a precise age by itself, but a strong clue about era. White dwarf cooling. Some clusters contain white dwarfs, which cool predictably over long times. Their temperatures can provide an independent clock. Nucleocosmochronology. In rare cases, abundances of certain radioactive elements can be used as long-term time indicators, though this is challenging and uncertain. No single method is absolute. But when multiple methods point toward similar ages for the oldest stellar populations, the universe's age story becomes stronger. And this is why dating stars matters so much for our documentary's main question. If the universe has a certain age, then the oldest stars should be somewhat younger than that age, because stars form after the early universe becomes structured enough to create them. So the oldest stars place a lower limit on cosmic age. The universe must be old enough to have formed and evolved stars of that age. They also provide a consistency check on expansion-based age estimates. If the age inferred from the cosmic microwave background and expansion history says the universe is, for example, around a certain number of billions of years, and the oldest globular clusters come out slightly younger, that coherence builds confidence. If they disagreed strongly, it would signal a serious problem. So stellar dating is part of the universe's self-consistency test. It ties together two completely different approaches. A global approach, age from expansion and early universe signals. A local approach, age from the lifetimes and evolution of stars. When those approaches agree, the cosmic story feels more real. Not because we are certain of every detail, but because different kinds of evidence converge on the same picture. And now, with that method in place, we are ready to return to one of the great boundaries of our observation again, because the universe has not only old stars, but also regions and events we cannot see directly. If light is our main messenger, then there are limits where light cannot tell us enough. There are edges to the observable universe. Not edges where space ends, but edges where information stops reaching us. So the next chapter moves from dating stars to understanding the largest observational boundary of all. The limits of the observable universe. How far we can see. Why that limit exists. And what it means for the question of age. Because beyond a certain point, the universe is not only older in our view, it becomes unreachable in principle. In the next chapter, we will step into those limits and understand why the universe's age is tied to horizons. Quiet boundaries that define what can ever be known. At first, the idea of the universe feels like a single thing. A vast space filled with galaxies, stretching outward without obvious end. And when we begin learning astronomy, it is easy to assume that if the universe is large enough, we could simply keep looking farther, seeing more and more, until eventually we would see everything. But the universe does not allow that. Not because our telescopes are too weak. Not because we have not built the right instruments yet. But because the universe has a built-in limit. A horizon created by time and by the speed at which information travels. There is a maximum distance from which light has had enough time to reach us since the beginning of the universe's current expansion history. Beyond that distance, light has not arrived. And in some cases, because of the way expansion behaves, light will never arrive. This is the boundary of the observable universe. It is not the edge of the universe itself. It is the edge of what can ever be observed from here. That distinction matters. Because the observable universe is often misunderstood as a bubble containing everything that exists. It is not. It is a bubble containing everything that can send us information in the form of light and other signals within the universe's lifetime. So when we talk about the observable universe, we are talking about a relationship between three things. The universe's age. The speed of light, the speed of information. The universe's expansion history. If the universe had been infinitely old, the observable region could be infinite. If information traveled instantly, the whole cosmos could be visible at once. But neither is true. The universe has a finite age. Information travels at a finite speed. And space itself has been expanding in ways that can increase the separation between distant regions even while light is traveling. So the horizon emerges naturally. It is the consequence of cosmic time. And this is where our documentary's question about age becomes sharper again. Because the observable universe is not only a limit in space. It is a limit in time. When you look far away, you look back. At greater distances, you see earlier cosmic eras. Eventually you approach the earliest visible era, the cosmic microwave background, light from the time when the universe became transparent. That is the practical visual boundary. But the observable universe is also defined by something deeper. The idea that there is a maximum amount of past we can access through signals. So there are two related boundaries. The surface of last scattering, the CMB, the oldest light we can see. The horizon of observation, the farthest distance from which any signal could have reached us since the universe began its expansion. These boundaries are connected, but they are not identical. And both of them remind us that the universe is not entirely available to observation, even in principle. This is difficult for the human mind because we tend to think that with enough technology, we can overcome any barrier. But the observable horizon is not a technical barrier. It is a causal barrier. A boundary created by the finite speed at which cause and effect can travel. So when we say, we cannot see beyond this, we are not saying, we haven't built a strong enough telescope. We are saying, there has not been enough time for information from beyond that boundary to reach us. And this has a quiet philosophical weight, but we do not have to treat it as philosophy. We can treat it as a practical truth about what knowledge is. There are regions of the universe whose existence we may infer, but whose direct signals cannot reach us. There are events that may occur beyond our horizon that we will never observe, no matter how long we wait, because the expansion of space can carry them away faster than their light can travel toward us. This is where dark energy, introduced earlier, becomes relevant again. An accelerating expansion implies that over time, more and more of the universe becomes causally disconnected from us. Not because it disappears, but because the space between us and it grows so quickly that signals cannot keep up. So the observable universe is not merely a snapshot of what exists. It is a changing boundary, one shaped by the universe's expansion. And this boundary influences how we think about age. Because when you say, the universe is this old, you are also implying a maximum depth of history you can ever observe. Age creates visibility. But age also creates limits. There is another important nuance here. Even within the observable universe, our ability to see does not mean we see everything that exists inside it. Some regions are hidden behind dust. Some objects are too faint. Some wavelengths are blocked by Earth's atmosphere. Some phenomena do not emit light we can detect. So there are practical observational limits that depend on technology. But those sit on top of a deeper limit that does not depend on technology at all. And that deeper limit is what this chapter is about. It is the boundary of causality, the boundary of arrival, the boundary of what can ever reach us. And once you accept that, the question, how old is everything we see, gains a new dimension. Because it is not only a question about time. It is a question about access. It asks, what does the universe allow us to know, given that knowledge must travel? How much of reality is visible? And how much remains beyond the horizon, not because it is hidden, but because it is too far in the wrong direction of time and expansion? This is not a reason for despair. It is a reason for clarity. A universe with horizons is not a universe that refuses knowledge. It is a universe that shapes knowledge. It sets boundaries, and within those boundaries, it offers us deep evidence, enough to reconstruct an extraordinary story. But if we want to go further, if we want to talk about what lies earlier than the oldest light or what lies beyond the observable horizon, we need new messengers. Light can only take us so far. And even within what light can show us, there is a boundary we cannot cross, the era before the universe became transparent. So the next chapter returns to that earliest visible surface and asks the natural next question. If the cosmic microwave background is the oldest light we can see, what lies beyond it? What lies earlier than visibility? And how do scientists even begin to talk about an era that cannot be observed with ordinary light? In the next chapter, we will approach the early boundary again, not as a repetition but as a deeper step, understanding what it means to reach a limit, and why the most important parts of the universe's history may be hidden behind a curtain we cannot lift with photons alone.